No one alive has ever seen these places as they were meant to be seen. We arrived thousands of years too late. The colors have faded, the roofs have fallen, and the voices of their builders disappeared long before history began to remember them. All that remains are fragments, towering walls, weathered temples, hidden chambers, and stones so precisely placed that they continue to challenge modern understanding. Every generation studies them with better technology than the last, yet the same silence remains. The monuments never explain themselves. They simply endure, inviting each new age to ask the same timeless questions. Perhaps that is why the ancient world still captivates us, not because it has preserved all the answers, but because it has preserved the mystery. Ostia Antica lies about 25 kilometers southwest of Rome, Italy, near the ancient mouth of the Tiber River. Systematic excavations beginning in the 19th century gradually uncovered one of the best preserved Roman cities ever found, revealing not only streets, warehouses, baths, and apartment blocks, but also an immense hydraulic network hidden beneath them. Archaeologists soon realized that almost every public fountain, bath complex, workshop, and drainage channel belonged to a single gravity-powered distribution system extending through the city, transforming Ostia into one of the clearest examples of an ancient settlement where gravity itself functioned as technology rather than merely a natural force. The city reached its greatest prosperity during the 2nd century AD, when its population is estimated to have exceeded 50,000 inhabitants, while serving as the principal harbour supplying Rome. Such a population demanded an enormous and continuous water supply without mechanical pumps. Fresh water arrived through aqueducts descending gently toward the city before entering elevated distribution reservoirs known as Castella Aquarum. From these reservoirs, gravity alone delivered water across an intricate network of lead pipes, terracotta conduits, masonry channels, fountains, baths, workshops, and private residences. Modern hydraulic calculations show that even a difference of only a few meters in elevation can generate sufficient pressure to supply an extensive urban network. Yet the remarkable feature at Ostia was not simply that water flowed downhill, it was that gravity simultaneously transported water, balanced pressure, regulated distribution, flushed waste, and maintained an entire urban infrastructure operating almost continuously for centuries. This immediately raises one of the greatest engineering mysteries surrounding Ostia. Every hydraulic system loses efficiency whenever demand changes, especially in a densely populated city where thousands of people may draw water simultaneously from different locations. Modern engineers solve this problem with valves, pressure regulators, sensors, and pumps. None of these technologies existed in Roman Ostia. Nevertheless, archaeological investigations have revealed surprisingly stable pipe dimensions, carefully positioned reservoirs, and repeated elevation changes that appear intentionally designed to preserve nearly constant hydraulic pressure throughout different districts. No surviving Roman engineering manual explains how builders calculated the relationship between reservoir height, pipe diameter, friction losses, and expected consumption with enough precision to prevent widespread pressure collapse. Although Roman authors such as Vitruvius described general construction principles, they never documented the mathematical procedures capable of designing a distribution network on this scale. Whether the engineers relied upon sophisticated empirical rules accumulated over generations or possessed surveying methods that disappeared with the empire remains unanswered. The mystery becomes even deeper when examining the gradients of the channels feeding the city. Water flowing too rapidly erodes masonry, damages joints, and increases turbulence that accelerates structural wear. Water flowing too slowly deposits calcium carbonate, sediment, and organic material that gradually block the conduits. Studies of Roman aqueducts show that many channels maintained gradients between approximately 0.1 and 0.3% over considerable distances, representing elevation changes measured in centimeters across hundreds of meters. Maintaining such consistency across uneven terrain required surveying accuracy astonishing even by modern standards. Ostia inherited this precision throughout its urban network despite constant rebuilding over several centuries. Surveyors possessed instruments such as the chorobates, the groma, and the dioptra, yet many historians question whether these devices alone could repeatedly achieve the uniform gradients preserved throughout the archaeological remains. No complete explanation has emerged describing how Roman engineers continuously transferred these measurements through an expanding city while avoiding cumulative surveying errors. As the network spread beneath new neighborhoods, gravity itself appears to have been manipulated almost like a programmable resource. Excavations have identified multiple distribution reservoirs positioned at carefully selected elevations rather than simply at the highest available locations. Hydraulic modeling suggests that each reservoir may have divided water into separate pressure zones before feeding different districts. Instead of allowing pressure to increase uncontrollably in lower areas, the system repeatedly interrupted the hydraulic head, effectively resetting pressure before water entered another section of the city. This principle resembles modern pressure management systems remarkably closely, yet no surviving Roman text identifies these structures as hydraulic regulators. Archaeologists continue debating whether their true purpose extended far beyond simple storage, because their locations correspond more closely with pressure balancing than with convenient water collection. Another unanswered question concerns the extraordinary reliability of the lead pipe network itself. Thousands of individual pipe sections connected beneath busy streets, public buildings, and private homes. Every joint represented a potential source of leakage capable of reducing pressure throughout the network. Yet excavated pipes frequently display carefully standardized diameters, remarkably consistent wall thicknesses, and sophisticated joining techniques that minimized water loss. Roman engineers even developed standardized pipe classifications known as fistulae, suggesting centralized control over hydraulic dimensions. What remains uncertain is how installers preserved watertight connections across an expanding city, experiencing seasonal temperature changes, soil movement, and centuries of continuous use. Modern municipal systems regularly require extensive maintenance despite advanced materials, while substantial portions of Ostia's underground infrastructure survived nearly 2,000 years beneath accumulated sediments. Gravity also performed another task, rarely appreciated today. It operated the city's sanitation system. Water overflowing from public fountains and bath complexes did not simply disappear into drains. Instead, surplus flow entered carefully aligned sewer channels where it continuously flushed waste toward the Tiber River. Rather than constructing separate energy systems for water supply and wastewater removal, Roman planners transformed a single gravitational resource into a self-sustaining hydraulic cycle. The more water entering the city, the more efficiently its underground sewers cleaned themselves. This elegant integration remains difficult to replicate because every additional connection changes hydraulic behavior elsewhere within the network. Whether Roman engineers intentionally modeled these interactions or gradually optimized them through generations of observation cannot be determined because the calculations behind their decisions have vanished entirely. Evidence from sediment deposits introduces another intriguing puzzle. Many ancient water systems eventually become clogged with mineral scale, biological growth, and accumulated debris. Calcium carbonate naturally precipitates from hard water, gradually narrowing channels and increasing hydraulic resistance. Surprisingly, several sections of Ostia's network contain less obstruction than hydraulic models predict after centuries of operation. Some researchers propose that builders deliberately alternated channel gradients, introducing periodic increases in flow velocity capable of carrying sediment away before significant accumulation occurred. Others argue that reservoir geometry itself generated controlled turbulence that reduced stagnation. Neither explanation has been conclusively demonstrated because the complete network no longer survives, preventing direct experimental reconstruction of its original hydraulic behavior. The city's continual expansion makes the engineering challenge even more remarkable. Ostia evolved over several centuries as warehouses, apartment buildings, markets, bath complexes, and industrial districts multiplied alongside growing commercial activity. Every new structure increased water demand while simultaneously altering pressure distribution across existing pipelines. Modern hydraulic engineers depend upon computer simulations to predict these interactions before extending municipal systems. Roman builders possessed neither digital modeling nor modern equations describing fluid dynamics. Even so, archaeological evidence indicates that new neighborhoods integrated into the existing network without triggering widespread hydraulic instability. Whether this reflects extraordinary practical experience or a sophisticated computational tradition now entirely lost, remains one of the most compelling unanswered questions in Roman engineering history. Lirb, also known as Seleucia, lies high above the Mediterranean coast in present-day Antalya province, Turkey, where its remarkably preserved water system was gradually documented through archaeological surveys during the 20th century after dense forest concealed much of the ancient city for centuries. Built at an elevation of roughly 450 meters on the southern slopes of the Taurus Mountains, the settlement possessed no large river flowing through its center, yet excavations revealed stone channels, terracotta pipelines, cisterns, settling basins, fountains, and distribution networks spread across the urban landscape. Their arrangement immediately raised an extraordinary question, because every major component depended entirely upon differences in elevation. No evidence of mechanical pumps, water wheels used for lifting, or pressure-driven machinery has been found. Gravity alone powered the entire system, transforming the natural landscape into an invisible machine that continuously transported, regulated, stored, and distributed water throughout the city. The more archaeologists reconstructed the network, the more remarkable its precision appeared. Water most likely originated from springs emerging higher within the Taurus foothills before entering carefully aligned conduits that descended toward the city. Modern hydraulic engineering shows that an open-channel system can function efficiently only within a narrow range of gradients. If the slope becomes too steep, water accelerates, creating turbulence capable of eroding channels, damaging joints, and carrying destructive sediment. If the gradient becomes too shallow, velocity drops below the level required to keep fine particles moving, eventually blocking the conduit. Engineers today calculate these values through equations describing flow velocity, friction, and discharge, yet Roman builders at Lirb achieved comparable practical results nearly 2,000 years ago without mathematical models or precision surveying equipment as understood today. The surviving channels rarely display signs of catastrophic erosion, suggesting that flow remained remarkably stable despite the difficult terrain surrounding the city. That observation leads directly to one of the greatest unanswered mysteries. The landscape around Lirb is far from uniform. Hills, limestone ridges, Shallow valleys and fractured bedrock interrupt what would otherwise be a straightforward route for gravity-fed water. Every deviation in elevation changes hydraulic behavior, maintaining continuous flow across several kilometers while preserving nearly constant gradients would have required repeated measurements with extremely small cumulative errors. Roman surveyors are known to have employed instruments such as the chorobates, the groma, and plumb lines, but none of these devices alone fully explains how gradients remained so consistent over rugged topography, where even minor mistakes could have stopped the entire system. Modern archaeologists can measure the finished network with laser scanning and digital elevation models, yet reconstructing the exact surveying process remains largely impossible because no engineering manual describing Loeb's construction has survived. The mystery deepens when examining how the city controlled hydraulic pressure without modern theory. Unlike a simple downhill ditch, an urban distribution system must deliver water gently enough to avoid rupturing pipes while maintaining sufficient pressure for fountains, baths, and public facilities located at different elevations. Pressure naturally increases with the height of the water column according to the relationship between elevation and hydrostatic force, meaning every additional meter changes the mechanical stress experienced by the pipeline. Excavated terracotta pipes from Roman Anatolia generally measured only a few centimeters in diameter and were joined with carefully fitted sockets sealed against leakage. At Loeb, many sections appear to have survived without evidence of repeated structural failure, suggesting that pressure remained within safe limits. Exactly how Roman engineers balanced elevation differences to prevent destructive pressure while preserving reliable flow has never been fully demonstrated through archaeology. Equally intriguing is the apparent role of reservoirs and settling basins scattered across the city. At first glance, they seem to function merely as storage facilities, yet their placement suggests a more sophisticated purpose. Modern hydraulic systems frequently employ intermediate reservoirs to stabilize pressure, reduce sudden fluctuations, remove suspended sediment, and regulate discharge before water enters smaller distribution lines. Several basins at Loeb occupy strategic elevations where incoming water could slow naturally before continuing downhill. This arrangement hints that gravity itself performed multiple engineering functions simultaneously. It transported water, filtered impurities through reduced velocity, stabilized pressure by buffering changes in flow, and then released cleaner water into the urban network. Archaeologists can observe the architecture, but whether these structures were intentionally designed as hydraulic regulators or simply convenient storage installations remains an unresolved debate because the original operating principles were never recorded. Sediment management presents another puzzle. Every spring carries dissolved minerals together with fine particles of clay, sand, and organic material. Left uncontrolled, these materials gradually accumulate until channels become obstructed. Yet several excavated sections indicate surprisingly limited long-term blockage, considering the centuries during which the network operated. Some researchers have proposed that subtle variations in channel width and depth intentionally altered water velocity so heavier particles settled within designated basins while cleaner water continued downstream. Similar principles are employed in modern sedimentation tanks, but proving deliberate hydraulic optimization in an ancient system is exceptionally difficult because the physical evidence consists only of stone channels whose original operating conditions can no longer be directly observed. Even computer simulations cannot reproduce every seasonal variation that affected the network during antiquity. The city's relationship with seasonal climate introduces another unanswered question. Southern Anatolia experiences pronounced differences between wet winters and dry summers, meaning spring discharge changes substantially throughout the year. A system designed only for maximum flow would struggle during drought, while one optimized for dry conditions could become destructive during periods of heavy rainfall. Nevertheless, Lieb supported public fountains, baths, domestic consumption, and everyday urban activity over generations. The surviving infrastructure suggests careful anticipation of fluctuating water availability. Yet, archaeologists cannot determine how Roman engineers estimated annual discharge or calculated storage capacity without continuous hydrological records. They evidently possessed practical environmental knowledge refined through observation, but the methods by which those observations became engineering decisions disappeared long ago. Perhaps the most remarkable realization emerges only after mapping the city as a whole. Public buildings, baths, fountains, cisterns, and principal streets align closely with the hydraulic network rather than appearing randomly distributed across the hilltop. This raises the possibility that gravity dictated urban planning itself. Instead of constructing buildings first and later solving the problem of water supply, the engineers may have established the hydraulic framework before determining where the city's major structures would stand. If so, gravity was no longer simply a natural force acting upon the settlement. It became the organizing principle behind the city's architecture, infrastructure, and daily life. Every building occupied a position defined by invisible lines of hydraulic potential extending across the landscape. Delos water system, Greece. On a small rocky island with no permanent river, gravity became the machine that kept an ancient city alive. Long before pumps, engines, or pressurized pipelines existed, the inhabitants of Delos transformed elevation itself into a source of energy, creating a hydraulic network whose precision continues to challenge archaeologists and hydraulic engineers. The remains of this forgotten system emerged gradually through excavations beginning in the late 19th century, when the French school at Athens uncovered streets, houses, cisterns, drains, fountains, and terracotta pipelines buried beneath centuries of collapse. What first appeared to be isolated water installations slowly revealed itself as a remarkably integrated network, extending across much of the urban landscape, raising an unsettling question. How did builders working more than 2,000 years ago calculate and preserve hydraulic gradients with such consistency across an uneven island without any modern surveying instruments? The mystery begins with the island itself. Delos covers only about 3.5 square kilometers in the center of the Cyclades and receives an average annual rainfall of roughly 350 to 400 millimeters, with almost all precipitation concentrated during the winter months. There is no perennial river capable of supplying an urban population. Yet by the 2nd and 1st centuries BCE, the island had become one of the busiest commercial ports in the eastern Mediterranean. Ancient estimates and archaeological studies suggest that its permanent population, together with merchants, pilgrims, sailors, and seasonal visitors, may have reached well over 15,000 people during periods of peak activity. Supplying such a population required far more than collecting rainwater. Water had to be captured, stored, distributed, conserved, and removed continuously despite months of seasonal drought, and every stage of that process depended almost entirely upon gravity. Excavations have identified hundreds of underground cisterns beneath private houses, public reservoirs, stone-lined channels, terracotta pipes, wells, drainage tunnels, and carefully engineered street gutters. Each individual component is impressive, yet the greater mystery lies in how these independent elements function together as one interconnected hydraulic organism. Rooftops directed rain into settling basins before water entered underground cisterns. Overflow channels prevented structural damage during heavy storms, by transferring excess water toward lower storage facilities instead of allowing it to flood buildings. Streets were designed not merely for movement, but also as controlled drainage corridors that guided runoff toward larger collectors. None of these processes required moving mechanical parts. Elevation alone controlled the entire sequence, turning the natural force of gravity into an invisible technology operating continuously throughout the city. The greatest unanswered question concerns the astonishing precision of hydraulic gradients maintained across Delos. Modern gravity-fed water systems depend upon carefully calculated slopes because water behaves unpredictably outside a narrow range. A channel that descends too steeply accelerates flow, producing turbulence capable of eroding joints, damaging masonry, and washing sediment into unwanted locations. A channel that is too flat allows suspended particles to settle, eventually clogging pipelines and reducing discharge. Modern engineers determine these gradients using surveying equipment capable of measuring differences in elevation to within millimeters. Yet no comparable instruments are known from Hellenistic Greece. Nevertheless, numerous surviving pipelines and drainage channels display gradients that remain remarkably consistent over long distances, despite crossing irregular bedrock and densely built neighborhoods. Archaeologists can measure the finished product, but they still cannot explain the surveying method that produced it. Did builders rely on water-filled trenches, suspended plumb lines, calibrated sighting frames, or techniques that have disappeared entirely from the historical record? No ancient manual describing such procedures has survived, leaving one of the most sophisticated aspects of the entire system unexplained. The challenge becomes even greater when considering that Delos was never built upon a flat plain. Its streets rise and fall around exposed granite outcrops, artificial terraces, and densely packed buildings constructed over generations. Every new house, workshop, or sanctuary altered local drainage patterns. Maintaining reliable gravity flow across such an evolving landscape required more than simply digging downhill. Engineers had to anticipate changes in elevation before construction began, ensuring that every additional structure remained compatible with an already functioning hydraulic network. In effect, the city itself became a three-dimensional hydraulic calculation carried out without modern mathematics, laser levels, or digital mapping. The remarkable coordination visible today suggests that builders possessed surveying knowledge far more advanced than the surviving written evidence indicates. Gravity also served another purpose rarely appreciated until recent hydraulic studies. It continuously cleaned much of the drainage system without requiring human intervention. During winter storms, increased runoff naturally accelerated through carefully proportioned channels, carrying accumulated sediment toward larger collectors before it could permanently obstruct narrower conduits. Hydraulic engineers describe this principle as self-flushing flow, yet Delian builders achieved the effect simply by controlling elevation differences and channel geometry. There were no mechanical gates opening at precise moments, and no manually operated flushing devices. Seasonal rainfall activated the cleaning cycle automatically, allowing gravity itself to maintain the health of the network. The fact that such passive maintenance was integrated into the original design demonstrates an understanding of flowing water extending well beyond simple transportation. Individual houses formed equally important components of this gravity-powered infrastructure. Many residences contained central courtyards surrounded by sloping roofs, directing rainfall into collection points connected with underground cisterns. Sediment settled before cleaner water entered storage chambers lined with waterproof hydraulic mortar. Once reservoirs reached capacity, overflow channels diverted surplus water toward neighboring drains, rather than allowing destructive pressure to accumulate beneath foundations. Every household therefore functioned as a miniature hydraulic station linked to the wider urban system. Instead of constructing one enormous reservoir supplying everyone equally, the inhabitants distributed storage across hundreds of smaller units interconnected by gravity. Such decentralization increased resilience during drought, because failure in one section did not necessarily disable the entire city. Equally intriguing is the balance maintained between freshwater supply and wastewater removal. Archaeological evidence indicates that clean water channels and drainage conduits were usually separated vertically and spatially, reducing opportunities for contamination despite the crowded urban environment. Achieving this separation demanded accurate control over relative elevations throughout the settlement. Freshwater needed sufficient hydraulic head to reach fountains and domestic storage areas, while wastewater had to continue descending without intersecting potable supplies. This delicate arrangement depended entirely upon topography rather than mechanical pressure. Gravity determined which direction every drop would travel long before it entered the network. The durability of the physical infrastructure presents another unresolved puzzle. Many terracotta pipes recovered from Delos retain joints that fit with extraordinary precision despite more than 2 millennia of earthquakes, seasonal expansion, salt-laden air, and ground movement. Their dimensions were standardized sufficiently to permit reliable assembly while remaining flexible enough to accommodate subtle shifts in the surrounding soil. Modern researchers understand the materials employed, yet the production tolerances consistently achieved across large numbers of ceramic components remain surprisingly sophisticated for an ancient manufacturing economy. Equally mysterious is the absence of widespread catastrophic leakage that would normally be expected from such an extensive gravity-fed network operating continuously for centuries. Akrotiri on the island of Thera, modern Santorini, Greece, remained hidden beneath volcanic ash for more than 3,000 years until systematic excavations led by the Greek archaeologist Spiridon Marinatos began in 1967. What emerged was not merely a Bronze Age town, but one of the most sophisticated hydraulic systems ever discovered from the 2nd millennium BC. Buried by the Great Minoan eruption around 1600 BC, the city had been sealed beneath ash thick enough to preserve streets, multi-story buildings, ceramic pipelines, drainage shafts, and underground sewers almost exactly as they existed on the day the settlement was abandoned. Archaeologists quickly realized that the greatest engineering achievement was not visible in the colorful frescoes or impressive architecture, but beneath the streets, where gravity itself had been transformed into a machine capable of moving fresh water, wastewater, and storm runoff across an entire urban landscape without pumps, gears, or any external source of power. The more researchers documented the underground network, the more extraordinary its design became. Excavated streets revealed stone-lined drainage channels running beneath carefully paved roadways, while large ceramic pipes carried wastewater away from houses through enclosed sewers. Some buildings stood 3 stories high and contained bathrooms connected directly to vertical terracotta pipes that discharged into underground collectors. Separate conduits supplied clean water from springs and cisterns, while entirely different channels removed sewage and rainwater, creating a remarkably advanced separation of water systems more than 3,500 years ago. Such a distinction would not become common in many European cities until the modern era, yet Akrotiri achieved it using nothing except elevation, carefully calculated gradients, and precisely positioned conduits. Gravity became the engine that regulated every movement of water throughout the settlement. That realization immediately raises the question that still divides engineers today. Maintaining continuous flow through gravity alone requires an extremely narrow range of gradients. If the slope becomes too steep, water accelerates faster than suspended waste, allowing heavier material to accumulate and eventually block the channel. If the gradient becomes too shallow, velocity decreases until water stagnates completely. Modern sewer systems therefore rely upon carefully surveyed inclinations, measured with optical instruments and laser equipment. At Akrotiri, however, surveyors more than 35 centuries ago produced underground channels extending across the settlement, while preserving gradients accurate enough for the system to function naturally. Archaeological measurements show that many conduits maintain remarkably consistent inclinations despite passing beneath uneven streets and densely constructed buildings. No surveying instruments, engineering manuals, measuring standards, or written instructions explaining how this precision was achieved have ever been recovered, leaving the practical method behind one of the world's earliest urban hydraulic systems completely unknown. The mystery deepens because the network was not constructed on an empty plain, but across terrain shaped by volcanic activity. Santorini consists of layers of lava, ash, pumice, and fractured bedrock created by repeated eruptions over thousands of years. Building underground channels through such geology would have required builders to anticipate differences in soil stability, groundwater movement, and structural loading long before modern geotechnical science existed. Yet excavations reveal drainage tunnels that remained sufficiently aligned even after centuries of seismic activity preceding the catastrophic eruption itself. Whether this durability resulted from accumulated experience, empirical geological knowledge, or sophisticated construction techniques passed through generations remains impossible to determine because the civilization left no technical descriptions explaining how its engineers evaluated the ground beneath the city. Even more puzzling is the deliberate variation in pipe dimensions throughout the network. Excavated ceramic pipelines do not maintain identical diameters from one end to the other. Some gradually narrow before widening again, while others connect through specially shaped junctions that appear designed to regulate flow rather than simply transport water. Modern hydraulic engineering recognizes that changing pipe diameter alters velocity, pressure distribution, and the ability of flowing water to remove sediment. Similar principles are incorporated into contemporary sewer and water management systems, yet the builders of Akrotiri accomplished comparable hydraulic control entirely through geometry. Archaeologists cannot determine whether these changing dimensions resulted from repeated practical experimentation or whether Bronze Age engineers already possessed mathematical rules governing fluid behavior that have since disappeared together with their written tradition. The houses themselves reveal an equally remarkable understanding of gravity. Several residences contain toilets connected to vertical drainage shafts, descending through multiple floors before entering underground collectors beneath the streets. The arrangement allowed wastewater to fall naturally through enclosed ceramic pipes, before joining larger sewers carrying it away from inhabited areas. The system required every vertical shaft, horizontal conduit, and underground collector to intersect at precisely calculated elevations. Even a small construction error could have caused reverse flow, flooding, or permanent blockage inside the buildings. Instead, archaeological evidence indicates that these domestic sanitation systems functioned successfully as part of the city's integrated infrastructure. This suggests that the engineers responsible for individual houses worked according to a unified hydraulic plan rather than independent local solutions. Yet, no evidence survives identifying who coordinated such complex urban design or how construction was organized across the settlement. Questions also surround the remarkable longevity of the drainage network before the volcanic catastrophe froze it in time. Ancient drainage systems normally suffer from sediment accumulation, root intrusion, structural collapse, or gradual deformation caused by ground movement. Akrotiri certainly experienced seasonal rainfall and volcanic earthquakes, yet its sewer network remained operational until the city was abandoned shortly before the eruption. Excavated inspection shafts and accessible maintenance points suggest that periodic cleaning formed part of the original design, but archaeologists still debate how maintenance crews detected obstructions within enclosed underground passages lacking modern access equipment. Whether specialized workers regularly inspected the system, or whether its hydraulic geometry naturally minimized sediment deposition, remains unresolved. Perhaps the greatest mystery lies not beneath the streets, but within the knowledge required to imagine such a city in the first place. During the 17th century BC, much of the contemporary world still depended upon open drainage ditches, simple cesspits, or natural runoff channels. Akrotiri instead integrated architecture, sanitation, urban planning, and hydraulic engineering into a single gravity-powered machine operating continuously beneath daily life. Every street, building foundation, stairway, and pipeline formed part of one interconnected system in which elevation replaced mechanical energy. The sophistication displayed by this buried city rivals engineering concepts normally associated with civilizations many centuries later, yet almost nothing survives explaining how such knowledge emerged or how it was transmitted. Ironically, the eruption that destroyed Akrotiri also preserved the evidence that continues to challenge modern understanding. The volcanic ash sealed pipelines before centuries of rebuilding, scavenging, or erosion could erase their original arrangement, allowing archaeologists to examine one of humanity's oldest intact urban hydraulic networks almost exactly as its engineers left it. They can measure the gradients, trace the conduits, reconstruct the flow paths, and calculate the hydraulic performance, but they still cannot answer the fundamental question: how did Bronze Age surveyors, working without modern instruments, transform nothing more than gravity and careful geometry into a city-wide technology capable of delivering water, removing waste, regulating flow, and sustaining thousands of people with a precision that remained hidden beneath volcanic ash for more than 3.5 millennia? Perja distribution towers in Antalya province, southern Turkey, emerged from excavation during the 20th century as archaeologists uncovered one of the best preserved Roman hydraulic systems in the eastern Mediterranean. What first appeared to be a collection of ordinary stone towers soon proved to be something far more sophisticated. Careful mapping revealed that these structures were not defensive towers at all, but distribution chambers positioned at carefully selected elevations, where incoming water from distant springs was divided and redirected throughout the city. Every excavation season added another section of channels, pipes, settling basins, and pressure control features, gradually exposing a network that functioned almost entirely through gravity. The discovery transformed Perja from an impressive Roman city into one of the clearest demonstrations that ancient engineers treated gravity not simply as a natural force, but as a controllable technology capable of replacing mechanical power. The water supplying Perja originated in the foothills of the Taurus Mountains, several kilometers north of the city. Instead of pumping water uphill or relying on mechanical devices, Roman engineers designed an aqueduct whose overall gradient remained remarkably gentle, generally only a few meters of elevation loss over every kilometer. Such precision prevented destructive acceleration while ensuring that the flow never lost enough energy to stop. Modern hydraulic engineering recognizes this balance as essential because excessive slope increases erosion and pressure, while insufficient slope allows sediment to accumulate until water stagnates. Maintaining this equilibrium across many kilometers without laser surveying equipment, optical levels, or electronic instruments remains one of the greatest unanswered questions surrounding the site. Archaeologists can calculate the gradients after construction, yet no surviving inscription, drawing, or engineering manual explains how Roman surveyors repeatedly achieved such extraordinary accuracy in the field. The greatest mystery begins when the water finally reached Perge itself. Rather than allowing it to flow directly toward fountains or baths, the aqueduct discharged into elevated distribution towers that functioned as hydraulic control centers. Every outlet sat at a carefully calculated height relative to the streets below. The elevation of each opening determined the hydraulic head available to the pipeline connected beneath it, meaning gravity alone established how much pressure every district would receive. Modern engineers express this relationship through hydrostatic pressure, where every meter of water column produces approximately 9.8 kilopascals of pressure. Although the Roman builders never described the principle mathematically, the towers demonstrate that they understood its practical consequences with remarkable precision. A difference of only 1 or 2 meters in outlet elevation could completely change the performance of fountains, baths, or residential water supplies. The unanswered question is not whether they mastered this relationship, because the architecture proves they did, but how they calculated it centuries before the scientific language of hydraulics existed. Excavation inside several distribution structures has revealed another puzzle that continues to divide specialists. The outlets are neither identical nor perfectly symmetrical. Some openings are noticeably wider than others, some are positioned at different elevations, and several appear deliberately offset rather than aligned. At first glance, the arrangement seems irregular. Yet computer simulations indicate that these variations may have been intentional. Larger openings reduce flow resistance while higher outlets decrease available pressure, suggesting that the towers may have balanced several hydraulic variables simultaneously. If this interpretation is correct, the builders were effectively regulating discharge rates across an entire urban network using geometry alone. No valves, pumps, or moving machinery have been found within these towers. Gravity continuously adjusted the system simply because every outlet occupied exactly the correct position. Whether Roman engineers relied on empirical testing accumulated over generations or possessed theoretical rules now completely lost, remains one of the most intriguing mysteries surrounding Perge. Even more remarkable is the apparent stability of the entire distribution system, despite the natural variability of spring discharge. Mountain springs rarely produce identical flow throughout the year. Seasonal rainfall, snowmelt, drought, and sediment all influence the volume entering an aqueduct. Under modern conditions, such fluctuations normally require mechanical regulation or automated controls to maintain consistent service. Yet archaeological evidence indicates that Perge continued supplying monumental fountains, public baths, ornamental basins, workshops, and residential districts without obvious signs of repeated reconstruction intended to compensate for unstable pressure. Some hydraulic researchers propose that the distribution towers themselves acted as pressure buffers. Their internal chambers may have temporarily absorbed fluctuations in flow before releasing water into outgoing pipelines at a steadier rate. Although this hypothesis matches several structural characteristics observed during excavation, no surviving Roman text explicitly confirms the purpose of these chambers, leaving one of the system's most advanced functions open to interpretation. The extensive use of lead pipelines introduces another engineering question that remains surprisingly difficult to answer. Lead pipes possess practical advantages because they are flexible, corrosion-resistant, and relatively easy to shape, yet they also fail when exposed to excessive internal pressure. If the hydraulic head inside purge exceeded safe limits, ruptures would have become inevitable. Instead, excavated sections demonstrate long-term service with relatively limited structural failure, considering nearly 2,000 years of burial and geological activity. This suggests that pressure throughout the network rarely exceeded the mechanical tolerance of the materials. Such control could only have resulted from extremely accurate management of elevation differences across the city. Modern hydraulic design routinely calculates these values through equations describing pressure loss, pipe diameter, roughness coefficients, and friction factors. No evidence indicates that Roman engineers possessed equivalent mathematical formulations, yet the finished infrastructure behaves as though similar relationships had already been understood in practice. The distribution towers also reveal evidence that water quality received as much attention as pressure management. Before entering secondary pipelines, water slowed inside settling basins where suspended sand and heavier particles naturally accumulated under gravity. This reduced abrasion within downstream pipes while improving water clarity before it reached fountains and households. The process required no filters or mechanical treatment because gravitational settling accomplished the task continuously. What remains uncertain is how builders determined the necessary dimensions of these chambers. If they were too small, sediment would continue downstream. If they were excessively large, flow velocity would decrease enough to encourage biological growth and stagnation. Excavated basins consistently fall within proportions that modern engineers recognize as effective for sediment removal. Yet the reasoning behind those proportions disappeared with the civilization that created them. Laser surveys of Pergi have further demonstrated that the hydraulic system was integrated into the city's urban planning from the very beginning, rather than added after construction. Streets, public squares, bath complexes, fountains, and drainage channels align with predictable hydraulic levels that maximize gravitational efficiency. This means the city itself was designed around moving water, rather than forcing water through an existing urban landscape. Such planning required surveyors to understand future pressure distribution decades before many buildings were completed. Every new structure depended upon elevations established long before its foundations were laid. The surviving architecture therefore preserves not merely isolated engineering achievements but an entire philosophy in which gravity became the invisible machine operating beneath daily life. Lothal, Gujarat, Western India. More than 4,000 years ago, a city built almost entirely from standardized fired bricks stood beside an ancient tidal channel connected to the Arabian Sea, where one of the most remarkable engineering traditions of the Bronze Age still challenges modern understanding. The ruins were identified during archaeological surveys by the Archaeological Survey of India in the early 1950s, and systematic excavations led by S.R. Rao between 1955 and 1962 uncovered an urban settlement of the Indus civilization dating mainly between about 2400 and 1900 BCE. What emerged was not simply another Harappan city, but a place where brick technology had been pushed to a level of precision that appears astonishing for a society without iron tools, modern surveying equipment, hydraulic cement, or written engineering manuals that can still be read today. From the beginning, Lothal revealed an unusual pattern. Houses, streets, drainage systems, wells, platforms, warehouses, and the massive basin commonly interpreted as a dockyard were all tied together by an extraordinary consistency in brick manufacture. Throughout much of the Indus civilization, bricks followed the famous 1:2 to 4 proportion of thickness, width, and length, allowing builders to combine them in countless structural arrangements while maintaining uniform bonding patterns. At Lothal, this standardization reached an impressive level. with thousands of surviving bricks showing only minimal dimensional variation, despite being produced centuries apart. Such consistency implies that builders relied on carefully controlled molds, repeated measurements, and organized production rather than individual craftsmanship alone. Yet no complete industrial complex capable of manufacturing the enormous quantity of bricks required for the city has ever been identified. Archaeologists have uncovered kilns associated with Harappan settlements, but none fully explains how millions of nearly identical bricks were produced while maintaining such strict dimensional accuracy across an expanding urban landscape. The mystery is not that ancient people could fire bricks, but that they sustained industrial-scale quality control long before any surviving evidence of centralized engineering administration. That achievement becomes even more remarkable when attention shifts toward the feature that has fascinated researchers for decades. Lothal stood beside tidal waterways where fresh water mixed with seawater, exposing its buildings to one of the harshest environments possible for fired clay. Salt is among the most destructive agents affecting masonry because dissolved minerals penetrate microscopic pores before crystallizing during evaporation, gradually forcing bricks apart from within through repeated expansion. Modern conservation projects spend enormous resources limiting this process, because even high-quality fired brick eventually suffers severe deterioration under continuous salt exposure. Yet substantial portions of Lothal survived nearly 4 millennia in precisely such conditions. Many bricks retain sharp edges, recognizable surfaces, and structural integrity despite repeated flooding, seasonal monsoon cycles, fluctuating groundwater, and long-term salt accumulation. Laboratory analyses confirm that Harappan builders selected fine alluvial clays and fired them at temperatures likely ranging between approximately 700 and 900 degrees Celsius. Although some researchers argue that certain batches may have reached even higher temperatures, depending on kiln conditions. Even with these estimates, the exact combination of clay composition, firing duration, oxygen control, and cooling process that produced such durable material remains uncertain. No surviving written records describe their manufacturing methods, leaving archaeologists to reconstruct the technology only through experimental archaeology. Every attempt demonstrates that slight differences in mineral content or kiln atmosphere dramatically affect long-term resistance to salt weathering, suggesting that Harappan brickmakers possessed practical knowledge refined through generations of observation, even if the scientific principles behind it were never formally recorded. The more closely the city is examined, the more difficult it becomes to dismiss this durability as simple coincidence, because the entire urban plan depended upon brick structures remaining stable despite unstable environmental conditions. Lothal occupied low-lying terrain vulnerable to flooding, forcing its inhabitants to elevate residential districts upon massive brick platforms while integrating sophisticated drainage channels beneath streets and buildings. Constructing such a system required careful calculation of gradients so that wastewater could continue flowing by gravity without eroding the surrounding foundations. Excavations revealed covered drains, inspection chambers, soak pits, and interconnected channels whose slopes remain remarkably effective despite thousands of years of geological change. Achieving these gradients without modern surveying instruments raises important questions about the measuring techniques available to Bronze Age engineers. Standardized weights and finely divided measuring scales discovered throughout the Indus civilization indicate an advanced understanding of precision, but exactly how surveyors transferred those measurements across an entire city remains unresolved. Even minor errors repeated over hundreds of meters would have caused stagnant water or structural failure, yet the surviving layout demonstrates a level of planning rarely associated with settlements of such antiquity. Attention inevitably returns to the enormous brick-lined basin that dominates Lothal because it represents one of the most debated structures in South Asian archaeology. Measuring roughly 214 meters in length and about 36 meters in width, with walls constructed from carefully laid fired bricks, the basin has long been interpreted as the world's earliest known dockyard by many researchers. According to this interpretation, engineers designed it to accommodate boats arriving through a channel connected to tidal waters while controlling sediment accumulation and fluctuating water levels. If correct, the walls would have been subjected not only to static water pressure, but also to currents, repeated wetting and drying, silting, and possible impacts from wooden vessels. Such conditions normally accelerate erosion, particularly where salt water is involved, yet substantial sections survived long enough to preserve the overall form of the structure. Other scholars argue that the basin may instead have functioned as an irrigation reservoir or water storage facility rather than a dock, demonstrating that its precise purpose remains controversial. Regardless of which interpretation ultimately proves correct, both explanations require brickwork capable of withstanding prolonged hydraulic stress, far beyond what would normally be expected from ordinary Bronze Age masonry. Equally intriguing is the relationship between Lothal and other Harappan cities scattered across more than 1 million square kilometers of the Indus civilization. Sites including Harappa, Mohenjo-Daro, Kalibangan, Rakhigarhi, and several others exhibit the same standardized brick proportions despite lying hundreds of kilometers apart across different ecological zones. Such uniformity implies that brick dimensions were governed by shared engineering traditions extending across one of the largest urban civilizations of the ancient world. Whether this consistency resulted from centralized political authority, standardized craft education, itinerant master builders, or deeply rooted cultural conventions remains unknown because the Indus script has not yet been deciphered. Until those inscriptions can be read with confidence, the organizational system that maintained this remarkable technological uniformity continues to remain hidden behind silence. Timgad, located in the Ourais Mountains of northeastern Algeria, about 35 kilometers east of modern Batna, first emerged again in the 18th century when European travelers reported extensive Roman ruins rising from the surrounding plain, while systematic excavations beginning in the late 19th century gradually uncovered one of the best preserved Roman cities ever found beneath centuries of wind-blown sediment. As archaeologists exposed its streets, forums, baths, temples, houses, and underground sewers, they realized the greatest achievement was hidden beneath the paving stones rather than above them. The city, founded by Emperor Trajan around AD 100, functioned as a vast hydraulic machine powered almost entirely by gravity. Every street, drain, public fountain, bath complex, and wastewater channel depended upon carefully controlled elevation differences instead of mechanical pumps. Gravity was not simply assisting the city, it was the technology that allowed every part of its urban infrastructure to operate continuously, yet the methods that made this possible remain only partially understood. The first mystery begins with the remarkable precision of the city's topography. Timgad occupies a gently sloping plateau, where natural elevation differences measure only a few meters across large sections of the urban grid. Modern surveys show that many Roman streets followed gradients close to 1% or even slightly less, steep enough to maintain flowing water, yet gentle enough to prevent destructive erosion. Civil engineers recognize that such slopes closely resemble those still recommended for modern gravity drainage systems, because they balance flow velocity against sediment deposition. Achieving this relationship across an entire city appears straightforward on modern digital terrain models, but Roman surveyors possessed nothing comparable. Their known instruments, including the chorobats for leveling, the groma for alignment, and the dioptra for angular measurements, were entirely mechanical. None offered the precision expected from laser levels or electronic total stations. Even a cumulative surveying error of only a few centimeters repeated across hundreds of measurements could eventually reverse drainage directions or create stagnant sections within the network. Excavation, however, reveals remarkably consistent hydraulic behavior throughout the surviving system. No surviving construction manual explains how Roman engineers transferred elevations across the expanding city while preventing accumulated error, leaving archaeologists to study the finished product without fully understanding the surveying process that produced it. That uncertainty becomes even greater beneath the streets themselves. Excavated sewer channels demonstrate that drainage was never designed as a collection of isolated pipes. Instead, every secondary drain gradually merged into larger collectors before directing wastewater toward the outskirts of the settlement. This hierarchy resembles modern branching drainage networks whose hydraulic efficiency depends upon continuously increasing carrying capacity. Many channels maintain dimensions that appear carefully matched to expected discharge from surrounding neighborhoods, rather than following identical standardized widths. Such proportional scaling suggests that engineers estimated future water volumes before construction even began. The challenge becomes extraordinary when considering that public baths, fountains, workshops, domestic courtyards, rainfall runoff, and seasonal storms all contributed different quantities of water throughout the year. There is no evidence that Roman engineers possessed mathematical hydraulic equations comparable to those developed during the 19th century, yet the network operated effectively for centuries. Whether these proportions resulted from generations of empirical experimentation or from engineering principles now completely lost remains impossible to determine, because no contemporary technical documents describing their calculations have survived. The mystery deepens when examining how the system appears to have minimized clogging, despite carrying both wastewater and sediment. Modern sewer engineering relies upon the concept of self-cleansing velocity, generally requiring flow speeds high enough to transport suspended material before it settles on the channel floor. If water moves too slowly, sediment accumulates until expensive maintenance becomes unavoidable. If it moves too quickly, erosion damages the infrastructure itself. Excavated drains at Timgad show surprisingly little evidence of repeated structural rebuilding caused by hydraulic failure, suggesting that flow conditions remained within a remarkably stable operating range. Archaeologists have identified inspection openings and maintenance access points in parts of the network, proving that cleaning certainly occurred, yet there is little indication of constant reconstruction across the entire city. This raises an unresolved question. How accurately could Roman builders predict water velocity using only practical observation? Experimental archaeology demonstrates that very small changes in gradient, sometimes only a few millimeters per meter, can significantly alter sediment transport over long distances. Somehow, the builders repeatedly selected slopes that maintained functionality without modern fluid dynamics, transforming gravity into a self-regulating maintenance system rather than merely a force moving water downhill. Equally intriguing is the relationship between the drainage system and the city's famous orthogonal street plan. Timgad is celebrated as one of the clearest surviving examples of Roman urban planning, with nearly rectangular blocks organized around the Cardo and Decumanus. At first glance, this appears to be an exercise in architectural order, yet the underground evidence suggests the grid also served hydraulic purposes. Straight streets simplified drainage alignment, reduced unnecessary bends, and allowed underground channels to maintain nearly continuous gradients beneath predictable routes. Buildings were therefore not positioned solely for military organization or aesthetic symmetry. They also occupied elevations compatible with the hidden hydraulic machine beneath them. Every public bath required wastewater removal, every fountain required overflow management, and every household depended upon storm runoff leaving the property without flooding neighboring structures. The visible geometry above ground may therefore represent only one layer of a much larger engineering design in which gravity dictated the organization of the city itself. Because the original planning records disappeared long ago, researchers still debate whether hydraulic requirements determined the street layout from the very beginning, or whether engineers adapted drainage after the urban plan had already been established. Another unresolved puzzle concerns the remarkable long-term stability of the network. Timgad experienced centuries of occupation before gradual decline, abandonment, and eventual burial beneath wind-blown sediment from the surrounding landscape. When French excavations intensified during the late 19th and early 20th centuries, many underground channels remained structurally intact, despite almost 2,000 years of environmental change. Seasonal rainfall, soil expansion, thermal stress, and occasional seismic activity normally produce gradual deformation capable of disrupting precisely graded drainage systems. Yet numerous sections preserved their original hydraulic geometry with surprisingly limited collapse. Roman builders clearly understood foundation preparation exceptionally well, even though they lacked modern geotechnical science describing soil mechanics or differential settlement. They selected bedding materials, masonry arrangements, and structural thicknesses capable of preserving gradients over many generations. How they evaluated ground stability before construction remains uncertain because no written explanation survives. Modern engineers can calculate bearing capacity using mathematical models and laboratory analysis, while Roman surveyors appear to have reached remarkably similar practical conclusions through methods now almost entirely invisible in the archaeological record. Water distribution itself introduces another level of complexity because gravity simultaneously powered supply and removal. Aqueducts delivered fresh water from higher elevations into reservoirs, fountains, and public baths before wastewater entered the drainage network below. These two systems had to remain carefully balanced. Excess supply could overload sewers during periods of heavy use, while insufficient supply might reduce flow enough to encourage sediment accumulation. The hydraulic relationship between incoming and outgoing water therefore required continuous equilibrium. Archaeological evidence demonstrates that Timgad contained numerous fountains distributed throughout residential districts, providing both public access to water and a steady contribution to drainage flow. Some hydraulic historians have suggested that continuous fountain overflow may have helped sustain minimum velocities inside the sewer network, even during dry periods, effectively allowing gravity to regulate cleaning as well as transportation. Although the concept appears plausible, direct documentary evidence confirming intentional hydraulic balancing has never been discovered, leaving researchers unable to determine whether this represented deliberate engineering strategy or an unintended consequence of Roman urban design. Knossos Drainage Network on the island of Crete, Greece, is one of the oldest surviving examples of a city where gravity itself became the machine. Hidden beneath the famous Minoan Palace lies an underground hydraulic network so carefully engineered that many researchers believe its greatest achievement was not the construction of walls or columns, but the invisible control of moving water without pumps, engines, or any external source of power. The first systematic investigation of the palace began in 1900, when British archaeologist Sir Arthur Evans started excavating the mound of Kephala near modern Heraklion. As rooms, staircases, courtyards, and workshops gradually emerged, archaeologists uncovered something they had never expected beneath a Bronze Age palace, dating mainly between roughly 1700 and 1450 BC. Running below floors and through walls was a sophisticated network of terracotta pipelines, stone-built sewers, inspection chambers, drainage channels, rainwater collectors, and vertical shafts connecting multiple levels of the palace. Instead of isolated drains serving individual rooms, the discoveries revealed an integrated hydraulic system extending across a complex covering nearly 20,000 square meters and rising through several stories. The realization transformed Knossos from an archaeological monument into one of the earliest known examples of large-scale hydraulic engineering. What continues to fascinate engineers is not simply that the Minoans transported water, but that they appear to have programmed gravity itself to perform every essential task. Fresh water descended naturally from higher springs through carefully aligned ceramic pipes. Rainwater disappeared into underground drains almost immediately after storms. Wastewater followed separate routes away from living quarters, while differences in elevation alone maintained continuous movement across the palace. Every drop obeyed gravity, yet gravity only worked because the builders first taught the landscape exactly how to guide it. The palace therefore functioned less like a collection of buildings than like a giant hydraulic mechanism whose moving parts were invisible beneath the stone floors. Long before machines converted fuel into motion, Knossos converted elevation into work. This idea raises the greatest mystery surrounding the entire complex. Gravity is perfectly predictable, yet only if every channel maintains an extremely precise gradient. A slope that becomes too steep accelerates erosion and damages the channel walls, while one that becomes even slightly too shallow allows sediment to settle until water eventually stagnates. Modern engineers achieve such accuracy with laser levels, optical surveying instruments, satellite positioning, and digital terrain models. The Minoans possessed none of these technologies. Their available equipment consisted primarily of ropes, measuring rods, plumb bobs, wooden frames, and bronze tools. Even with simple instruments, maintaining nearly continuous gradients through twisting corridors, beneath staircases, across changing elevations, and between multiple stories would have demanded extraordinary surveying precision. Archaeologists understand the final result because the channels still exist, but the exact surveying methods capable of producing such consistency nearly 4,000 years ago remain unknown. The ceramic pipelines themselves reveal another level of engineering that appears remarkably advanced for the Bronze Age. Rather than manufacturing identical cylindrical tubes, Minoan craftsmen produced pipes with a tapered profile, each section slightly wider at one end and narrower at the other. This allowed every pipe to slide securely into the next, producing tighter joints capable of resisting leakage while accommodating pressure differences along the network. Some specialists have noted that the conical design distributes stress more effectively than simple straight joints and reduces the likelihood of displacement if surrounding soil shifts. Crete lies within one of the most seismically active regions of the eastern Mediterranean, where earthquakes have repeatedly damaged settlements throughout recorded history. Whether the tapered joints were intentionally designed to tolerate ground movement, or whether this resilience emerged as an unexpected advantage remains uncertain, yet the system survived numerous destructive events that reshaped the palace itself. Even more intriguing is evidence suggesting that portions of the drainage network may have cleaned themselves automatically. Certain channels narrow before opening into broader sections, increasing water velocity as gravity forces the same volume through a reduced cross-sectional area. Higher flow speed generates greater shear stress along the channel floor, making it more difficult for mud and organic debris to accumulate. This principle resembles the self-cleansing velocity used in modern sewer engineering, where designers attempt to keep water moving fast enough to transport sediment before deposits can form. Whether the Minoans calculated these hydraulic effects mathematically or refined them through generations of observation cannot be determined, but the geometry of several surviving drains strongly suggests they understood that the shape of a channel could influence the behavior of flowing water. In other words, they were not merely building passages for water, they were shaping the water itself. The palace becomes even more astonishing when viewed as a complete hydraulic organism instead of separate architectural spaces. Fresh water, rainwater, and wastewater did not simply share convenient routes underground. They occupied different pathways with carefully controlled relationships to one another, minimizing contamination while ensuring reliable drainage throughout residential, ceremonial, and storage areas. Such separation required every conduit to intersect others at appropriate elevations without disrupting flow. Every staircase introduced another change in level. Every courtyard altered surface runoff. Every new building phase demanded adjustments without destroying the existing hydraulic balance. The deeper archaeologists examine the palace, the clearer it becomes that water management was not added after construction, but integrated into the original conception of the complex. This observation has inspired one of the most provocative interpretations of Knossos. Many researchers now suspect that the hydraulic network may actually have determined the architecture rather than the opposite. Instead of constructing buildings first and inserting drains wherever space remained, Minoan planners may have established the principal water routes, calculated gradients across the hillside, identified collection points, and only then organized walls, rooms, and courtyards around that invisible infrastructure. If true, gravity was not merely supporting daily life inside the palace. Gravity served as the primary design principle governing the entire settlement. Every room occupied its position because water needed to travel somewhere else first. Although direct written evidence has never been discovered to confirm this planning sequence, the remarkable integration between architecture and hydraulics continues to encourage that possibility. Natural topography also played a crucial role in this achievement. Knossos occupies gently sloping terrain overlooking the surrounding valley, providing enough elevation difference to sustain movement without producing destructive torrents. The builders appear to have exploited every subtle contour of the landscape, allowing the earth itself to provide energy continuously and without interruption. Unlike later civilizations that increasingly depended upon mechanical lifting devices, the Minoans invested extraordinary effort in understanding how gravity could replace machinery entirely. Once the system had been constructed correctly, the palace required no fuel, no animals, and no human labor to keep water moving through much of the network. Gravity worked every hour of every day with complete reliability, making the landscape an active component of the technology itself. The disappearance of this hydraulic knowledge remains one of Knossos's greatest mysteries. After the decline of Minoan civilization, around the middle of the 15th century BC, the palace gradually lost its importance. Although later civilizations built impressive water systems, few matched the seamless integration of architecture, surveying, and gravity seen at Knossos. With no surviving engineering records, archaeologists can study the finished network, but still cannot explain exactly how its builders achieved such remarkable precision. Quiquel, known today as Gemila in northeastern Algeria, stands more than 900 meters above sea level on a rugged mountain plateau where Roman engineers created one of North Africa's most sophisticated gravity-powered urban water networks. Excavations that began in the early 20th century uncovered aqueducts, underground conduits, stone channels, settling basins, fountains, public baths, and an extensive drainage system woven directly into the city's streets, revealing that almost every movement of water depended entirely on elevation rather than mechanical force. What initially appeared to be ordinary Roman hydraulic engineering gradually exposed a deeper puzzle. Every surviving structure suggests that gravity itself functioned as the city's invisible engine, yet many of the calculations that made such precision possible remain beyond complete archaeological explanation. The more researchers reconstruct the network, the more difficult it becomes to understand how ancient surveyors transformed one of the most challenging landscapes in Roman Africa into a machine powered only by the natural descent of water. Unlike cities established across broad plains, Kwikule occupied a steep terrain where streets climbed and descended across multiple ridges before converging around the forum. Such topography should have made reliable water distribution exceptionally difficult. Even a small error in gradient could have caused water either to accelerate violently and damage masonry, or to slow until flow stopped entirely. Modern hydraulic engineering often relies on laser surveying and digital elevation models to maintain gradients measured in only a few millimeters per meter. Yet Roman builders achieved remarkably stable water movement using simple instruments such as the chorobates, groma, plumbline, and measuring rods. Archaeological surveys indicate that many sections of the channels maintain slopes generally between approximately 0.1 and 1%, depending upon local terrain, allowing water to travel continuously while minimizing erosion and sediment accumulation. The remarkable consistency of these gradients across a city built on uneven mountain slopes remains one of the least understood aspects of the entire system, because no engineering manual survives to explain how thousands of measurements were transferred accurately from one construction phase to another. The mystery becomes even greater when the water reached the city itself. Gravity alone could not simply deliver water from an aqueduct into every neighborhood, because the natural elevation differences continuously changed hydraulic pressure. Excess pressure would have burst joints or eroded channels, while insufficient pressure would have left fountains and baths dry. Excavated remains reveal carefully positioned distribution basins, overflow channels, settling tanks, and branching conduits that appear to have moderated flow before water entered different districts. Instead of relying upon valves, pumps, or powered regulators, the entire hydraulic balance depended upon carefully calculated differences in elevation. Every basin acted simultaneously as a storage reservoir, sediment trap, pressure regulator, and distribution center, allowing gravity to perform several engineering functions at once. Although archaeologists can identify these structures, they still cannot reconstruct the mathematical process that determined the exact height of every outlet, nor explain how builders repeatedly achieved hydraulic equilibrium without instruments capable of measuring pressure directly. As researchers continued mapping the city, another unexpected pattern emerged. Kwikule did not remain frozen in a single period of construction, but expanded gradually from the 1st century through the 3rd century AD, as population increased and new public buildings appeared. Additional baths, temples, markets, fountains, and residential quarters demanded larger quantities of water, yet evidence suggests that the original hydraulic network was not abandoned whenever expansion occurred. Instead, new conduits were connected seamlessly into older infrastructure, while maintaining stable circulation across the entire settlement. Modern engineers normally redesign hydraulic networks extensively whenever demand changes because every additional branch alters flow rates and pressure throughout the system. At Kwikle, however, successive generations appear to have enlarged the network without triggering widespread hydraulic failure. Whether Roman engineers anticipated future expansion from the beginning or repeatedly recalculated the entire system using methods now lost remains an unanswered question. The absence of construction documents leaves archaeologists able to observe the finished network but unable to reconstruct the intellectual framework that allowed its continuous evolution. The fountains provide another challenge to conventional explanation. Throughout the city, public fountains occupied different elevations and varying distances from the primary supply channels. Yet archaeological evidence indicates that many maintained remarkably consistent water levels over long periods of operation. Achieving this balance without mechanical regulation required precise control over hydraulic head, because even small differences in elevation could dramatically change discharge velocity. Some fountains appear to have received water only after passing through intermediate reservoirs that absorbed pressure fluctuations before redistributing flow toward lower sections of the city. Others incorporated overflow arrangements that automatically removed excess water before pressure reached damaging levels. Gravity, therefore, became far more than a transport mechanism. It operated simultaneously as the pump, the pressure controller, the timing system, and the safety device, all without moving mechanical parts. Exactly how Roman surveyors predicted these complex interactions before construction remains one of the most debated aspects of ancient hydraulic engineering. Equally impressive was the relationship between the clean water supply and the drainage network beneath the streets. Excavations demonstrate that stormwater, wastewater, and fresh water generally followed separate pathways despite sharing the same confined urban landscape. Such separation demanded careful vertical planning because every conduit competed for limited underground space while still requiring continuous downward gradients. If one channel crossed another at the wrong elevation, contamination or backflow could have occurred, particularly during periods of heavy rainfall. Yet many surviving drains continued functioning for centuries with surprisingly limited evidence of catastrophic failure. Stone-lined channels directed runoff away from streets, while underground sewers carried wastewater downhill without interrupting the distribution of potable water above. This suggests that Roman engineers understood not only how gravity moved water, but also how different forms of water could be organized into independent systems operating simultaneously within the same terrain. The principles behind that integrated planning remain largely theoretical because no written explanation accompanies the physical remains. Perhaps the most overlooked mystery lies in the remarkable durability of the network itself. Nearly 2,000 years of earthquakes, seasonal floods, temperature variation, and structural collapse have damaged many buildings, yet significant portions of the hydraulic infrastructure still preserve their original alignment. Stone channels continue following carefully planned gradients, drainage passages remain recognizable beneath collapsed streets, and many conduits exhibit surprisingly limited deformation considering the unstable mountain environment. Modern hydraulic systems frequently require continuous maintenance to compensate for ground movement and material fatigue, whereas much of Kwikle's network survived centuries after the city itself declined. Researchers continue investigating whether the builders intentionally selected exceptionally stable geological layers, compensated for natural settlement through flexible construction techniques, or simply benefited from an extraordinary understanding of local terrain that has never been fully reconstructed. Southern Iraq. Rising from one of the flattest floodplains on Earth, the ancient city of preserves a paradox that becomes more astonishing the closer archaeologists examine its walls. Most of what survived for more than 4,000 years was not carved from granite or limestone, but built from earth itself, using millions of mud bricks and fired bricks that should have dissolved back into the alluvial plain long ago. Excavations led by Sir Leonard Woolley between 1922 and 1934 revealed not only the famous royal tombs, but also the immense ziggurat of Ur, whose surviving core exposed construction methods that continue to challenge modern assumptions about the limits of early brick technology. The city flourished during the early dynastic and Ur III periods, especially under King Ur-Nammu around 2100 BCE, when enormous public works transformed the urban landscape. Archaeological surveys estimate that the ziggurat originally stood more than 30 meters high, with a rectangular base measuring approximately 62 by 43 meters. Constructing a monument of that scale required several million bricks, each weighing several kilograms, meaning tens of thousands of tons of material had to be manufactured, transported, lifted, and precisely assembled without iron machinery, cranes, or wheeled construction equipment capable of carrying such immense loads. What makes the project remarkable is not simply its size, but the extraordinary consistency of the building material itself. Across large sections of the monument, bricks display nearly identical dimensions, standardized proportions, and stamped inscriptions naming Ur-Nammu, suggesting production was organized according to strict specifications that resemble industrial quality control far more than the irregular craftsmanship normally associated with the early Bronze Age. As excavations expanded beyond the ziggurat, archaeologists discovered that this standardization extended across much of the city. Residential districts, temples, administrative buildings, defensive walls, and paved streets were constructed with carefully selected combinations of sun-dried mud brick and kiln-fired brick, rather than relying on a single material. Laboratory analyses show that the bricks were primarily composed of fine alluvial clay mixed with silt and organic temper, such as chopped straw, reducing shrinkage during drying while increasing structural stability. Even so, recreating bricks with identical longevity has proven difficult because many experimental replicas begin cracking or deteriorating after decades of exposure, whereas original bricks from Ur have survived more than 4 millennia despite repeated cycles of seasonal flooding, salt crystallization, extreme summer temperatures exceeding 50 degrees Celsius, and occasional winter rainfall. The question is no longer whether the Sumerians understood brickmaking, but how they achieved a level of material performance that still cannot be reproduced with complete confidence. This mystery becomes even deeper when attention shifts from the bricks themselves to the thin black layers binding them together. Throughout the ziggurat and other monumental structures, excavators found extensive use of natural bitumen placed between courses of brick. At first glance, it appears to be a simple adhesive, yet detailed studies have demonstrated that it performed several critical engineering functions simultaneously. Bitumen formed an effective waterproof barrier that prevented rainwater from penetrating deep into the brick core, reducing erosion of the vulnerable mud brick beneath. It also acted as a flexible bonding layer, capable of absorbing minor structural movement caused by temperature fluctuations or gradual settlement of the soft floodplain below. Unlike rigid mortar, which tends to crack under repeated expansion and contraction, bitumen retained enough elasticity to distribute stress across large surfaces. This combination dramatically slowed the destructive process that normally reduces ancient mud brick architecture to featureless mounds within centuries. What remains unexplained is how the builders recognized these properties with such precision. Natural bitumen sources existed throughout Mesopotamia, yet different deposits possess different chemical compositions, viscosities, and weathering characteristics. Analyses suggest that the material used at Ur was carefully selected and sometimes heated before application, indicating deliberate processing rather than casual collection. No surviving Sumerian text describes the complete procedure. No workshop preserving the full manufacturing sequence has been identified, and no written technical manual explains why specific layers required bitumen while others did not. Modern engineers understand why the system works after measuring its physical behavior, but the intellectual path by which Bronze Age builders discovered this remarkably effective waterproofing technology remains almost entirely invisible. Whether the knowledge emerged through centuries of experimentation or through an organized tradition of empirical engineering passed between generations is still unknown. The effectiveness of this waterproofing becomes even more impressive because the ziggurat stands on deep alluvial sediments deposited by the Euphrates River, ground that would normally experience differential settlement under enormous weight. Instead of constructing directly on unstable soil, the builders created multiple foundation layers composed of compacted earth, carefully arranged brick platforms, and engineered fill that distributed pressure across a much broader surface. Even after thousands of years, surviving sections reveal surprisingly limited structural distortion compared with what many modern models predict for a monument of similar mass resting on comparable sediments. Researchers continue debating whether the builders intentionally calculated load distribution through accumulated experience or whether repeated observation across earlier construction projects gradually refined techniques that later reached their highest expression at Ur. Evidence from across the city suggests that brick technology was never treated as a single universal formula. Scientific sampling indicates noticeable differences between bricks intended for foundations, exterior walls, monumental architecture, drainage systems, and ordinary domestic buildings. Variations in clay composition, firing temperature, density, and organic additives imply that builders deliberately adjusted material properties according to structural function. Such specialization reveals a sophisticated understanding of engineering long before formal scientific terminology existed. Yet the criteria guiding these choices remain largely speculative because the written records emphasize administration, religion, and royal achievements while saying remarkably little about the technical knowledge that made those achievements possible. The remarkable preservation of countless individual bricks introduces another unresolved puzzle. Many still retain fingerprints left by workers who pressed wet clay into wooden molds more than 4,000 years ago, before the bricks hardened under the Mesopotamian sun or inside kilns. Those impressions survived not because they were protected inside sealed chambers, but because the surrounding material remained stable enough to preserve microscopic surface details despite relentless environmental stress. Salt migration, wind erosion, thermal expansion, and occasional flooding should have erased such delicate traces many centuries ago. Instead, they remain embedded within bricks that continue to hold their shape, offering silent evidence that the manufacturing process achieved an exceptional balance between hardness and resilience. The ancient city of Xanthos rises above the Xanthos River Valley in southwestern Turkey, where archaeologists first began systematic excavations during the 19th century, before extensive scientific investigations throughout the 20th century revealed an unexpectedly sophisticated drainage network hidden beneath streets, courtyards, and public buildings. Standing roughly 60 meters above the surrounding floodplain, the city occupied a naturally defensive limestone ridge, yet this advantageous position created a hydraulic challenge that should have made long-term urban life difficult. Seasonal Mediterranean storms could release enormous volumes of rain within only a few hours, sending water racing down steep rock surfaces with enough force to erode foundations, undermine walls, and flood inhabited districts. Instead of resisting gravity, the builders transformed it into the invisible engine that controlled every movement of water across the settlement. Excavations uncovered carefully aligned stone channels, underground conduits, street drains, collection basins, and discharge outlets arranged into a continuous network whose operation depended entirely upon differences in elevation rather than mechanical devices. Gravity became the technology itself, allowing the city to regulate runoff, transport wastewater, and protect its monumental architecture for centuries without pumps or external power. Yet the methods used to design such a precise hydraulic landscape remain among the least understood achievements of ancient Lycian engineering. The first unanswered question begins with the remarkable precision of the network's gradients. Modern hydraulic systems rely upon surveying instruments capable of measuring elevation differences with millimeter accuracy, because even slight deviations can dramatically alter flow velocity. If a channel descends too steeply, turbulent water rapidly erodes masonry, while a slope that is too shallow allows sediment to accumulate until the system becomes blocked. Archaeological measurements indicate that many surviving channels at Xanthos maintained gradients gentle enough to avoid destructive erosion while remaining steep enough to sustain continuous flow, despite crossing irregular limestone terrain where natural elevation constantly changes. Surveyors today would accomplish such work with laser levels, total stations, and digital elevation models. The Lycians possessed none of these technologies during the 5th and 4th centuries BC, yet they produced a network capable of functioning across an entire urban landscape. No inscriptions describe their surveying procedures, no measuring instruments have been identified with certainty, and no engineering manuals survive to explain how repeated elevation calculations were transferred from planning to construction. The finished system demonstrates remarkable geometric control, while the intellectual process behind that control has disappeared completely. As archaeologists traced additional sections beneath later Roman rebuilding, another mystery gradually emerged from the layout itself. The drainage channels rarely followed the shortest possible route downhill. Instead, they repeatedly curved, widened, narrowed, divided, and rejoined before finally reaching lower discharge points beyond the city walls. From a modern engineering perspective, these changes appear surprisingly intentional because each modification influences water velocity, hydraulic pressure, and sediment transport. Sharp acceleration would have damaged stone joints, while uncontrolled convergence could have overwhelmed downstream passages during heavy rainfall. Rather than allowing gravity to act without restraint, the builders seem to have guided its energy through a sequence of carefully balanced transitions that reduce destructive force while preserving uninterrupted movement. Similar hydraulic principles appear in contemporary flood control engineering, yet no physical evidence explains how ancient designers predicted the behavior of thousands of liters of stormwater moving simultaneously through interconnected underground passages. Without mathematical flow models, laboratory experiments, or modern fluid mechanics, they somehow created a self-regulating system whose performance depended entirely upon natural gravitational forces. The geological setting introduces another puzzle that continues to challenge researchers. Xanthos occupies fractured limestone bedrock shaped by tectonic activity, seasonal groundwater movement, and centuries of weathering. Such terrain is rarely uniform beneath the surface, meaning that hidden fractures or unstable layers could gradually shift foundations and alter drainage gradients. Nevertheless, significant portions of the underground network remained aligned closely enough to function even after more than 2,000 years of earthquakes, rebuilding, and abandonment. Southwestern Turkey lies within an active seismic region where destructive earthquakes have repeatedly affected ancient settlements throughout history. Stone walls collapse, pavements deform, and monuments tilt under these conditions. Yet several drainage passages preserved their original hydraulic logic despite surrounding architectural damage. Some researchers propose that builders intentionally anchored channels into the most stable bedrock, rather than relying upon artificial fill, but this explanation immediately raises another question. Identifying mechanically stable geological layers normally requires experience gained through systematic observation or geological investigation. How ancient engineers recognized those hidden structural advantages without modern geological science remains unknown, because the construction decisions reveal practical knowledge that exceeds anything recorded in surviving historical sources. The relationship between surface streets and hidden infrastructure provides another remarkable indication that gravity was treated as an active technological resource, rather than a passive natural force. Excavated road surfaces reveal subtle transverse slopes directing rainwater towards stone-lined gutters before transferring it into underground conduits through carefully positioned openings. This arrangement prevented uncontrolled sheet flow from spreading across public spaces while simultaneously reducing erosion around building foundations. Every street, therefore, became part of the hydraulic machine instead of existing independently from it. Water followed predetermined routes from roofs, courtyards, paved roads, and public spaces before entering progressively larger channels beneath the city. The entire urban plan appears organized around gravitational movement, suggesting that architecture and drainage were conceived together from the earliest planning stages, rather than added separately afterward. Yet, archaeologists cannot determine whether this integration resulted from written engineering plans, standardized construction traditions, or accumulated practical experience transmitted orally across generations. The absence of documentary evidence leaves the organizational system behind one of Lycia's most sophisticated urban infrastructures almost entirely invisible. Excavation has also revealed puzzling interruptions within the drainage network itself. Certain conduits terminate unexpectedly beneath later construction without preserved outlets, while other passages disappear beneath unexcavated sectors of the ancient city. These missing connections prevent researchers from reconstructing the complete hydraulic circuit and leave open the possibility that the surviving network represents only part of a much larger system extending beneath structures that remain buried. Some missing sections may have been dismantled during Roman rebuilding, while others could still lie concealed beneath accumulated archaeological deposits several meters thick. Ground-penetrating radar and geophysical surveys have identified anomalies consistent with additional underground features, yet excavation has not progressed far enough to verify every suspected connection. Consequently, modern reconstructions remain partly hypothetical, making it impossible to determine the original carrying capacity of the system or the precise sequence through which gravity distributed stormwater across different districts of the city. Every newly exposed channel answers one engineering question while creating several more concerning the overall hydraulic design. Kalibangan, on the southern edge of the Thar Desert in Rajasthan, India, preserves the remains of an Indus Valley city where one of the ancient world's greatest engineering puzzles was not carved into stone, but molded from clay. Excavations beginning in the early 1960s by the Archaeological Survey of India revealed a fortified settlement occupied from the early Harappan period around 3500 BC and flourishing during the mature Harappan phase between approximately 2600 and 1900 BC. What first appeared to be ordinary mud brick ruins gradually exposed an unexpected level of technological control, because nearly every structure seemed to follow the same invisible mathematical rules, raising a question that still has no complete answer. How did a Bronze Age society standardize millions of bricks across an entire city with a precision resembling an organized industrial system? As archaeologists cleared the defensive walls, residential blocks, wells, streets, fire altars and drainage features, they noticed that the dimensions of the bricks repeated with remarkable consistency. Whether made from sun-dried mud or fired in kilns, most bricks followed the famous Harappan proportion of 1 to 2 to 4, with thickness, width and length maintaining almost identical ratios throughout the settlement. This was not simply a convenient shape for stacking walls, because the same proportional standard also appears at Harappa, Mohenjo-daro, Rakhigarhi, Dholavira, and numerous other Indus cities, separated by hundreds, sometimes more than 1,000 kilometers. Maintaining a common standard across such an enormous geographical area would have required measurement systems, manufacturing discipline, and quality control far beyond what is usually associated with Bronze Age urban societies. Yet no written engineering manuals, official regulations, or administrative records explaining this remarkable uniformity have ever been discovered. The mystery becomes even deeper when the scale of production is considered. Kalibangan required countless bricks to construct fortification walls several meters thick, domestic buildings, public platforms, wells, drainage channels, and ritual structures, meaning that hundreds of thousands, and likely millions, of individual bricks had to be produced over generations. Every stage demanded consistency, from selecting suitable clay to mixing temper, forming molds, drying the bricks under controlled conditions, and firing selected batches without excessive cracking or distortion. Even minor variations in moisture or temperature can significantly alter the final dimensions of a fired brick. Yet the archaeological evidence suggests an astonishing level of uniformity. Modern engineers achieve comparable consistency through calibrated molds, controlled kilns, and standardized measurement tools, while Kalibangan accomplished it more than 4,000 years ago using technologies that remain only partially understood. No large industrial brick-making complexes capable of supplying the entire settlement have been identified with certainty, leaving researchers uncertain whether production was centralized, distributed among specialized workshops, or coordinated through an administrative system that has disappeared without trace. This extraordinary standardization did not exist merely for visual order, because the city itself appears to have been designed around the dimensions of the bricks. Wall thicknesses commonly correspond to exact multiples of brick widths. Corners meet at carefully planned right angles, and buildings fit together according to repeating modular measurements rather than improvised construction. Instead of cutting bricks to fit completed walls, the evidence indicates that architects designed the entire urban layout according to the dimensions of standardized units before construction even began. This modular approach minimized waste, simplified repairs, and ensured structural stability, principles that remain fundamental in modern engineering. The existence of such planning implies surveyors capable of measuring large areas accurately, builders trained to follow shared construction rules, and administrators able to enforce those standards across multiple generations. Yet none of the instruments or documents that would explain this organizational achievement have survived. Equally intriguing is the deliberate distinction between mud bricks and fired bricks throughout the settlement. Most walls and defensive structures relied on carefully manufactured mud bricks, while fired bricks were reserved primarily for wells, drains, water-related installations, and selected ritual platforms where resistance to moisture or repeated heating became essential. Rather than firing every brick, which would have demanded enormous quantities of fuel in an environment where timber was limited, the builders applied advanced material selection by matching each type of brick to the mechanical demands of its location. Such decisions reveal an empirical understanding of compressive strength, water resistance, and thermal durability that was developed centuries before the emergence of formal engineering science. Archaeologists continue to debate how this knowledge accumulated because no experimental workshops or technical texts survive to explain the principles behind these remarkably efficient choices. Kalibangan's circular wells illustrate this sophisticated understanding with exceptional clarity. Unlike straight walls, circular masonry requires each brick to contribute evenly to the overall geometry, while resisting outward pressure from the surrounding soil. The wells were constructed using specially shaped wedge-like fired bricks, arranged in concentric rings, that maintained almost perfect circular alignment from top to bottom. Even a slight error repeated through dozens of courses would gradually distort the structure, creating weaknesses that could eventually cause collapse. Instead, many of these wells have preserved their form despite more than 4 millennia of weathering, seasonal temperature changes, and shifting desert sediments. Archaeologists have never recovered the measuring devices, templates, or construction guides that would explain how Bronze Age builders repeatedly achieved such geometric accuracy under field conditions. The surrounding environment makes these achievements even more difficult to explain. Kalibangan lies in a region where summer temperatures frequently exceed 45 degrees Celsius, while winter nights can become comparatively cold, producing continual cycles of expansion and contraction within building materials. Strong desert winds transport abrasive sand capable of gradually eroding exposed surfaces, and occasional seasonal rainfall introduces additional stresses as moisture penetrates mud brick walls before evaporating again. Under such conditions, poorly manufactured bricks normally crack, deform, or disintegrate within relatively short periods, yet substantial portions of Kalibangan's brick architecture remained identifiable until excavation thousands of years later. Scientific analyses have confirmed that the builders carefully selected local alluvial sediments, although the precise mixture of clay, sand, and organic temper responsible for the brick's long-term durability remains uncertain. Proposed ingredients include straw, chaff, grasses, and animal dung, but no universally accepted formula has emerged from laboratory research, leaving the material science behind their success only partly understood. Among the site's most distinctive features are the brick-built fire altars discovered inside both residential and fortified sectors. These installations consist of carefully shaped brick platforms containing central pits that preserve evidence of repeated burning, including charcoal, ash, and animal bones. Their construction required bricks capable of withstanding recurring thermal stress without rapidly fracturing, suggesting careful control over firing temperatures and raw materials. Whether these installations served ritual ceremonies, controlled industrial activities, or functions that have not yet been recognized, remains a subject of continuing debate. The uncertainty is significant because their repeated appearance according to consistent architectural patterns indicates deliberate planning rather than random household activity, implying that the same technological standards governing the city's walls also extended into specialized structures whose precise purpose has yet to be fully explained. Çatalhöyük, on the Konya Plain of central Turkey, preserves one of the oldest cities on Earth, where thousands of homes built almost entirely from unfired mud brick have survived for nearly 9,000 years, despite being made from a material that should have disappeared long ago. The site first came to international attention in the late 1950s, when British archaeologist James Mellart identified the immense Neolithic mound, and systematic excavations beginning in 1961 revealed an urban settlement occupied between approximately 7,400 and 6,200 BCE. covering nearly 13 hectares at its peak and housing an estimated 5,000 to 8,000 inhabitants. Instead of broad streets, the city consisted of tightly packed rectangular houses entered through openings in their roofs, creating an uninterrupted landscape of mud brick architecture unlike anything known from the same period. Yet beneath this remarkable layout lies a technological mystery that remains far more difficult to explain than the city's unusual design, because the very material from which it was built should not still exist after almost 9 millennia. Modern adobe is generally considered a temporary building material. Even under favorable climatic conditions, unfired mud brick gradually loses strength as rainfall dissolves clay bonds, groundwater transports soluble minerals, repeated wetting and drying produces cracks, and seasonal temperature changes weaken the structure from within. In many parts of the world, mud brick buildings require continual maintenance simply to survive for a few generations, while abandoned structures often deteriorate rapidly once roofs collapse and walls become exposed to the weather. At Çatalhöyük, however, archaeologists continue to excavate walls, partitions, ovens, platforms, storage rooms, and complete floor plans whose original mud bricks remain recognizable after roughly 9,000 years. Individual bricks still preserve their dimensions. Wall alignments remain sufficiently intact to reconstruct entire neighborhoods, and microscopic studies continue to identify plant fibers embedded within the original construction material. The contradiction is obvious. According to conventional expectations, these bricks should have eroded into indistinguishable sediment thousands of years ago. Yet large portions of the settlement still retain architectural details precise enough to reveal how people organized their homes, explaining that extraordinary longevity has become one of the most intriguing questions surrounding ancient mud brick technology. Laboratory analyses indicate that the bricks were produced primarily from locally available clay-rich sediments mixed with water and chopped organic temper such as straw or other plant fibers, before being shaped in simple molds and dried naturally beneath the sun. Nothing about these ingredients appears revolutionary. Similar mixtures continue to be used across arid regions today, yet modern reproductions rarely approach the long-term durability demonstrated at Çatalhöyük. Experimental archaeology has shown that relatively small changes in clay mineral composition, particle size distribution, moisture content, drying duration, or fiber concentration can significantly influence compressive strength and resistance to cracking, but no combination has fully reproduced the exceptional preservation observed at the site. Some researchers suggest that the local alluvial sediments contained unusually favorable mineral proportions, while others argue that generations of accumulated practical knowledge allowed Neolithic builders to refine production methods through experience rather than formal science. Even so, the precise balance of variables responsible for the brick's remarkable stability remains unknown. The evidence suggests that ancient builders consistently achieved a level of material optimization that modern experiments have not completely duplicated, raising the possibility that subtle techniques vanished long before they could ever be recorded. The mystery becomes even greater when considering how these bricks supported an exceptionally dense urban environment for more than 1,000 years. Houses shared adjoining walls, creating continuous architectural blocks that distributed structural loads across entire neighborhoods instead of isolated buildings. Most walls measured between 30 and 50 centimeters thick, while interior platforms, hearths, storage bins, and elevated sleeping areas were integrated directly into the mud brick framework. Every roof also functioned as a public pathway because residents moved across the city from above rather than through streets at ground level. This meant that the walls beneath had to support not only the weight of the roof itself, but also the repeated movement of people carrying food, water, construction materials, and household goods every day. Such loading conditions would normally accelerate structural fatigue in unfired earthen construction, yet widespread catastrophic collapse is not evident throughout the archaeological sequence. Instead, buildings were repeatedly repaired, rebuilt, and incorporated into new construction without losing the overall stability of the settlement. Even more puzzling is the way the city continuously rebuilt itself upon its own remains. Rather than expanding outward across the surrounding plain, the inhabitants frequently demolished aging houses, filled interiors with compacted debris, leveled the surface, and erected new mud brick buildings directly above earlier generations. This process gradually produced the archaeological mound visible today, more than 20 meters high in places and containing numerous superimposed construction phases accumulated across approximately 14 centuries of occupation. Building repeatedly on older mud brick should have created serious foundation instability because compressed organic material, fragmented walls, and uneven settlement normally generate structural deformation. Yet excavation demonstrates that successive buildings remained remarkably well aligned. Floors stayed level enough for daily life. Walls rarely display the extreme differential movement expected from unstable foundations, and the settlement continued functioning without evidence of large-scale engineering failures. Exactly how Neolithic builders evaluated ground stability before constructing each new house remains uncertain, but their decisions repeatedly proved successful over many centuries. Another unresolved question concerns the striking uniformity of construction throughout the settlement. Archaeologists have documented consistent brick sizes and recurring wall proportions across numerous excavation areas, despite the absence of metal measuring tools or centralized industrial production. Such standardization would have simplified repairs, improved wall stability, and allowed adjoining structures to connect with surprising precision. Whether this consistency emerged through shared cultural tradition, communal training, or some form of informal measurement system has never been fully established. Whatever the explanation, the city displays an unexpectedly disciplined approach to construction that challenges common assumptions about technological capabilities during the Neolithic period. The interior finishing techniques introduce another layer of complexity. Many walls were repeatedly coated with fine white plaster, sometimes receiving dozens or even well over 100 separate applications during the lifetime of a single building. These surfaces remained smooth enough to support elaborate wall paintings, symbolic installations, and sculpted reliefs, while continuous replastering helped preserve structural integrity by sealing small cracks before they expanded. Chemical analyses identify lime-rich plasters combined with carefully prepared sediments, yet researchers still debate how ancient craftsmen consistently achieved such durable adhesion without modern additives. The repeated maintenance clearly reflects sophisticated building practices, but the exact procedures that maximize the lifespan of both plaster and mud brick remain only partially understood. Environmental conditions certainly helped preserve Çatalhöyük, but they cannot fully explain its remarkable survival. Central Anatolia receives relatively low annual rainfall, reducing water damage, yet the settlement has still endured nearly 9,000 years of seasonal temperature changes, erosion, and natural weathering. Many Neolithic mud brick sites in similar climates have eroded into indistinct mounds, while Çatalhöyük still preserves recognizable walls and floor plans. This suggests that its extraordinary durability resulted not from climate alone, but from a unique combination of raw materials, construction techniques, maintenance practices, and architectural design that modern researchers still cannot fully reconstruct. Nippur, Iraq. Thousands of ordinary mud bricks created one of humanity's longest-lasting sacred cities, yet the knowledge that made them endure has never been fully recovered. Hidden beneath the plains of central Mesopotamia, Nippur remained buried for centuries until systematic excavations, led by the University of Pennsylvania, beginning in 1889, revealed immense temple platforms, city walls, canals, administrative buildings, and more than 50,000 cuneiform tablets. As archaeologists gradually removed millions of cubic meters of accumulated earth, they discovered that the city's greatest achievement was not carved in stone, but built almost entirely from sun-dried mud bricks, a material normally expected to dissolve within decades under harsh weather. Instead, layer after layer of construction survived across nearly 4,500 years, forcing researchers to confront a technological tradition that appears far more sophisticated than its humble material suggests. Unlike many ancient capitals built around royal power, Nippur occupied a unique position as the spiritual center of Sumer and later Mesopotamian civilizations because it housed the Ekur temple dedicated to Enlil, the supreme deity of the Sumerian pantheon. From approximately 3500 BC until the early centuries AD, successive Sumerian, Akkadian, Ur-3, Babylonian, Kassite, Assyrian, and later rulers rebuilt the sacred precinct without abandoning its original location. This extraordinary continuity means that the archaeological mound accumulated more than 20 major occupation levels, creating a tell exceeding 20 meters in height across an area of roughly 90 hectares. Every rebuilding phase depended on enormous quantities of bricks, suggesting that hundreds of millions of individual units may have been produced during the city's lifetime. The obvious question is not why ancient builders used mud bricks, since stone was scarce across southern Mesopotamia, but how a city constructed primarily from unfired earth continued functioning for millennia despite seasonal rainfall, groundwater, salts carried upward by evaporation, and repeated flooding from nearby river systems. As excavations expanded, researchers noticed that the dimensions of bricks remained remarkably consistent through long periods of history. Many examples measure roughly 30 to 35 centimeters square and 7 to 10 centimeters thick, with variations expected between dynasties, but an overall degree of standardization that would have greatly simplified large-scale construction. Such consistency implies careful control over molds, drying conditions, and manufacturing practices across generations separated by centuries. No surviving text, however, explains who enforced these standards, or how knowledge passed uninterrupted through repeated political collapse. Empires disappeared, dynasties fell, and languages evolved, yet the practical technology behind the bricks changed surprisingly little. Archaeology can measure the finished products with precision, but the organizational system responsible for maintaining that consistency remains almost entirely invisible. Even more puzzling is the composition of the bricks themselves. Laboratory analyses consistently identify clay-rich alluvial sediments as the primary ingredient, but microscopic examination frequently reveals additional materials deliberately mixed into the matrix. Chopped straw is common, acting as reinforcement that reduces shrinkage during drying, while fragments of reeds, grass fibers, fine sand, silt, and occasionally ash are also present. None of these ingredients is individually mysterious, because similar additives are known from many ancient societies. The real mystery lies in their proportion and consistency. The mechanical behavior of mud bricks changes dramatically when only a small percentage of organic material is added or removed. Excess straw weakens compressive strength. Insufficient fiber allows severe cracking. Too much sand reduces cohesion, and excessive clay increases shrinkage. Modern earthen construction often requires repeated testing before achieving reliable performance, yet the builders of Nippur produced countless bricks capable of supporting monumental architecture with remarkable regularity. Archaeologists can identify what entered the mixture, but they still cannot reconstruct the precise recipes, moisture content, mixing sequence, or curing procedures that generated such dependable results. No cuneiform tablet recovered from Nippur provides a technical manual explaining how master builders balanced these variables, leaving one of the most fundamental aspects of Mesopotamian construction hidden behind thousands of years of silence. This uncertainty becomes even more significant when considering the scale of structures standing upon those bricks. The Ekur complex dominated the sacred landscape through repeated reconstructions, while surrounding temples, administrative buildings, and defensive works imposed enormous loads on foundations resting within unconsolidated river sediments. Modern engineers understand that saturated alluvial soils are prone to settlement, differential movement, and structural instability unless loads are carefully distributed. Excavation records nevertheless indicate that many successive rebuilding phases followed the footprints of earlier monuments, rather than abandoning weakened foundations altogether. Builders often raised the level of entire districts by adding compacted fills before laying fresh courses of bricks above previous construction. The result was not a chaotic accumulation, but an engineered sequence that preserved sacred orientation while maintaining structural stability. Exactly how ancient surveyors evaluated the bearing capacity of buried ruins remains uncertain because no surviving instruments or written explanations describe the process in sufficient detail. Water management created another engineering challenge. Southern Mesopotamia received relatively modest annual rainfall, generally between 100 and 200 millimeters, yet periodic storms, irrigation overflow, and fluctuating groundwater posed constant threats to mud brick architecture. Excavations at Nippur revealed carefully planned drainage systems, baked brick channels in vulnerable areas, and layered construction techniques designed to separate moisture from critical walls. Fired bricks, which demanded substantial fuel resources, were used selectively where water exposure or concentrated structural stress justified the additional expense. Doorways, drains, pavements, and hydraulic features often display baked bricks while ordinary walls remained sun-dried. Such selective deployment demonstrates an advanced understanding of material performance rather than indiscriminate building practices. The decision to reserve expensive fired bricks for critical locations reflects engineering judgment that resembles modern optimization of structural resources. The city's continual rebuilding also produced one of its most fascinating archaeological puzzles. Instead of demolishing older architecture completely, successive generations frequently buried deteriorating buildings beneath carefully prepared fills before constructing directly above them. This process gradually elevated the city's surface over thousands of years, while simultaneously preserving earlier phases beneath later ones. From an engineering perspective, however, stacking massive mud brick monuments upon older mud brick ruins should have introduced severe instability. Yet numerous walls remained aligned across multiple occupational levels, suggesting that ancient builders possessed reliable methods for consolidating underlying deposits before new construction began. The techniques may have involved staged compaction, controlled drying, or careful selection of fill materials, but direct evidence remains frustratingly incomplete because the construction process itself rarely survives, only its finished results. Thousands of stamped bricks recovered from Nippur add another layer of complexity. Many bear royal inscriptions identifying rulers responsible for temple restoration, often invoking divine protection from Enlil. These inscriptions were impressed before drying, requiring builders to orient each brick correctly during construction so the text remained legible upon completion. On isolated examples, this would be trivial, but across monumental platforms containing hundreds of thousands or even millions of bricks, maintaining consistent orientation implies disciplined planning, standardized work procedures, and careful supervision. The inscriptions reveal who commissioned construction yet remain almost silent regarding the craftsmen who transformed raw river mud into an enduring architectural system. Modern science has revealed that Nippur's bricks were made from local alluvial clay mixed with carefully selected natural materials, and experimental archaeology has shown that similar bricks can still be reproduced. Yet making a single brick is very different from sustaining a city for thousands of years. Researchers still cannot explain how ancient builders maintained such consistent quality on a massive scale without modern measurements or written engineering manuals, leaving one of Nippur's greatest technological achievements unresolved. Located along the southern Bug estuary in modern Ukraine, one Greek city transformed metal into a source of power. This was Olbia Pontica, a colony on the northern Black Sea where trade, coinage, and metallurgy became almost inseparable. Its ruins were not found as a buried wonder under desert sand, but as a wounded landscape near the village of Parutine. Professional excavations began in 1901 under Boris Farmakovsky, revealing walls, inscriptions, coins, workshops, and a lower city partly damaged by erosion and water. Olbia was founded by Greek colonists from Miletus in the 7th century BC. At its height, the city covered about 50 hectares, with an upper town, a lower harbour zone, sanctuaries, streets, defensive walls and workshops facing one of the most important river mouths of the Black Sea. From here, grain, fish, slaves, hides, timber and raw materials could move south toward the Greek world, while wine, oil, pottery, luxury objects and finished goods moved back towards Scythian lands. But beneath this trade network was a deeper question. How did a remote colonial city maintain the technical skill needed to turn metal into money? Tools, status objects, weapons, fittings, weights, and exchange goods for centuries. Olbia was not just a port, it was a machine for transforming resources into trust. The most famous clue is strangely small, the bronze dolphin money of Olbia. Around the late 6th century BC, the city began producing cast bronze objects shaped like leaping dolphins. They were not ordinary round coins struck with dies like many Greek currencies. They were cast, repeated, recognizable, and tied to the cult of Apollo Delphinios. Their shape looked symbolic, but their function was practical. They allowed value to circulate in a frontier market where Greeks, Scythians, merchants, sailors, farmers, and craftsmen all needed a common language of exchange. This is where the metallurgy becomes mysterious. Casting hundreds or thousands of small bronze dolphins required more than artistic imagination. It required a stable alloy, repeated molds, controlled melting, predictable cooling, and enough standardization for people to accept the objects as money. Bronze normally requires copper mixed with tin or other elements. Copper melts at about 1085 degrees Celsius, while bronze can be cast at slightly lower working temperatures depending on the alloy. Achieving that repeatedly in small furnaces using charcoal, bellows, clay crucibles, and human judgment was not simple. A few degrees too low, and the metal would not flow cleanly into the mold. Too much oxygen, and the surface could become flawed. Too much impurity, and the object could crack, shrink, or vary in weight. The mystery is not that ancient people could melt metal. Many cultures did. The mystery is how Olbia turned that skill into a commercial system. A single craftsman can make one beautiful object. A trading city needs repeatable production. It needs metal suppliers, fuel, mold makers, furnace operators, inspectors, merchants, and people who understand weight, purity, and trust. Yet the full technical chain has not survived. We have the coins, the fragments, the tools, the slag, and the archaeological context, but not the operating manual. Some excavations show how dense this monetary world was. In the T4 sector of Olbia, research from excavations in 2018 to 2020 recorded 154 coins, with about half of them being dolphin-shaped pieces. One hoard included 26 cast dolphin coins together with bronze items. That kind of find suggests that the dolphins were not isolated ritual curiosities. They were part of daily accumulation, exchange, and storage. The same city also produced larger cast bronze coins. Some 5th century Olbian bronze issues were massive compared with ordinary pocket money. One type reached about 69 millimeters in diameter and roughly 136 grams in weight. A coin that large is not convenient for casual use. It looks closer to a heavy unit of civic value, almost a metal statement. It raises a technical problem. Casting a large bronze disc evenly is harder than casting a tiny token. The metal must enter the mold without freezing too early, air must escape, the surface must cool without destructive stress, and the final object must remain recognizable enough to be accepted. Olbia's metal economy probably depended on both local and imported resources. The northern Black Sea region offered access to steppe networks, river routes, and contact with communities that could supply hides, animals, grain, and possibly raw materials. But tin, high-quality copper, and certain finished goods often moved through long-distance trade. That means Olbia's metallurgists were working inside a supply chain that stretched far beyond the city walls. The technical challenge was not only heating metal, it was managing inconsistency. Different copper sources can contain different traces of arsenic, lead, silver, nickel, or iron. Different fuel quality changes furnace temperature. Different crucibles affect contamination. Still, the finished objects had to be reliable enough for commerce. This creates one of Olbia's strongest ancient engineering questions. How did its workshops judge metal quality without modern chemical analysis? They had no spectrometer, no digital thermometer, no industrial furnace gauge. Their tools were color, sound, weight, smell, surface texture, fracture behavior, and experience. A skilled founder could read the glow of a melt, the fluidity of the pour, the skin forming on the surface, and the sound of a cooled object when struck. This was a scientific system without written formulas, transmitted by practice rather than textbooks. The harbour made that system valuable. Olbia's lower city, now partly submerged or eroded, was closely connected with docking, storage, and craft activity. Studies of the harbour area use inscriptions, graffiti, architectural remains, and finds from the lower city to reconstruct how the port functioned. Yet the artificial harbour facilities are only partly understood. If goods arrived by river and sea, metal objects had to be produced, weighed, repaired, exchanged, and possibly recycled near the commercial zone. Broken tools could become scrap. Scrap could become new bronze. Coins could move into hoards, temples, markets, or foreign hands. In such a world, metallurgy was not a separate craft. It was the nervous system of trade. The city's position made this even more complex. Olbia stood between the Greek world and the Scythian steppe. Greek merchants understood coinage, contracts, temples, and civic identity. Steppe elites valued metal differently, as weaponry, ornaments, horse gear, status display, and portable wealth. Olbia had to speak both languages. Its metallurgists may have produced objects that were technically Greek, but commercially adapted to frontier exchange. The dolphin money itself reflects that hybrid world, sacred symbol, civic marker, and practical bronze object at the same time. The archaeological record also suggests a wide craft environment. Olbia had potters, masons, woodworkers, metalworkers, and traders. These crafts supported one another. Potters could produce ceramic molds or furnace parts. Woodworkers supplied handles, bellows frames, ship repairs, and packing material. Masons built workshops and hearths. Traders brought ore, scrap, ingots, tools, and foreign models. Every bronze dolphin was therefore the final visible result of many invisible trades. What remains unexplained is the level of coordination. A metal workshop needs charcoal in large quantities. Charcoal production requires wood and controlled burning. Furnaces need clay linings that can survive repeated thermal shock. Bellows require leather and carpentry. Crucibles must resist heat and chemical attack. Molds must be prepared, dried, fired, and broken or reused. If the city produced coinage across generations, then Olbia had an industrial rhythm, even if it did not look like a modern factory. There is also the problem of trust. In any ancient marketplace, metal could deceive. A bronze object might look valuable but contain too much lead. A silver coin could be plated, a weight could be slightly wrong, a cast token could be copied. For Olbia's metal money to function, people needed confidence in the issuing authority, the symbol, the alloy, and the expected value. This means metallurgy was tied to law, religion, and civic power. The Temple of Apollo Delphinios, the dolphin symbol, and the city's commercial identity may have worked together to make metal believable. Over time, Olbia changed. It survived wars, pressure from surrounding peoples, economic shifts, and Roman influence. The city lasted from the archaic Greek period into the 4th century AD, but its most distinctive technical traditions did not survive as living systems. The harbour deteriorated, the lower city was damaged by water and erosion, workshops disappeared, the people who knew the alloy recipes, furnace behaviour, mould preparation, and commercial rules vanished without leaving a full written explanation. Located in modern-day Jublains in northwestern France, the massive Roman fortress appears at first glance to be just another late imperial military installation. Yet, from the moment archaeologists began systematically excavating the site in the 19th century, they encountered a paradox. The walls were among the strongest ever built in Roman Gaul, but almost everything inside suggested that the structure was never intended to function as an ordinary fortress. More than a century of excavations, aerial photography, laser scanning, geophysical surveys, and architectural analysis have revealed a monument that continues to challenge historians. Nearly 17 centuries after its construction, the greatest mystery is no longer who built it. It is why Roman engineers devoted such extraordinary resources to a building whose true purpose remains uncertain. The fortress was erected around the late 3rd or early 4th century AD, during one of the Roman Empire's most unstable periods. Germanic incursions threatened the Rhine frontier, civil wars erupted between rival emperors, and provinces throughout Gaul strengthened their defences. Yet Jublains stood roughly 500 kilometres from the nearest frontier. Unlike famous military centres such as Hadrian's Wall or the Rhine forts, it lay deep inside territory that had been securely Roman for nearly 3 centuries. Archaeological surveys have uncovered no evidence of a major siege, no widespread destruction layer, and no battlefield surrounding the complex. Nevertheless, Roman authorities invested an astonishing amount of labour into constructing one of the strongest fortifications in Western Gaul. The outer walls reached nearly 4 meters in thickness, reinforced by massive corner towers and carefully engineered gateways. Such dimensions rival defensive works built in regions facing constant military danger, raising an obvious question. why build a fortress capable of resisting a major assault where almost no enemy army was expected to arrive? The mystery becomes even deeper after crossing the walls. A normal Roman castellum followed a highly standardized layout developed over centuries of military experience. Archaeologists would expect to find long barracks capable of housing hundreds of soldiers, granaries elevated above damp ground, workshops, kitchens, wells, stables, administrative headquarters, and large open courtyards for training. Instead, Jublains offers surprisingly little of this. Excavations revealed relatively few internal buildings, almost no evidence for a permanent garrison of significant size, and remarkably limited traces of prolonged military occupation. The enormous defensive shell encloses an interior that appears strangely empty. It's almost as if Roman engineers concentrated their greatest efforts on protecting something that has since disappeared, rather than on accommodating troops. Some researchers have compared this contradiction to constructing a modern nuclear bunker with almost no living quarters inside. The architecture simply does not match its apparent function. One increasingly discussed hypothesis suggests that the fortress protected not soldiers, but wealth. During the Roman period, Jublain served as the capital of the Diablintes, an important administrative district complete with temples, baths, a theatre capable of seating several thousand spectators, forums, and government offices. Tax revenues, official archives, military payrolls, or imperial supplies may have been stored here. Such facilities would have required exceptional protection without necessarily housing a large army. Comparable secure storage complexes existed elsewhere in the empire, although few matched Jublain's in defensive sophistication. Yet this theory introduces another puzzle. Despite decades of excavation, archaeologists have discovered no treasury, no large concentrations of coins, no archive rooms, and no secure vaults that definitively explain the fortress's immense defensive capability. If valuable materials were indeed stored here, they vanished almost completely before history recorded their fate. Equally impressive is the engineering itself. Modern laser surveys demonstrate that many surviving walls remain remarkably straight despite standing for nearly 1,700 years. Some sections still rise over 8 meters high, while their vertical deviation measures only a few centimeters. Such precision required extraordinary control over foundation preparation, stone cutting, and load distribution. Roman engineers achieved this without steel reinforcement, powered cranes, hydraulic concrete pumps, or modern surveying instruments. Instead, they relied upon simple devices including plumb lines, measuring rods, the groma for establishing straight alignments, and the chorobates for leveling. Compared with modern construction tolerances, maintaining structural stability over walls nearly 4 meters thick across centuries of weather, freeze-thaw cycles, and ground movement represents an astonishing engineering achievement. The mortar itself continues to attract scientific attention. Like many monumental Roman buildings, the fortress employed opus caementicium *. The famous Roman concrete composed of lime, volcanic or local aggregates, crushed stone, and carefully graded filler materials. Electron microscopy and mineralogical analyses of Roman concretes elsewhere have revealed complex chemical reactions producing durable calcium-aluminum silicate hydrates that continue strengthening long after construction. While Jublains did not benefit from the volcanic ash available around the Bay of Naples, its builders adapted regional materials to create a remarkably resilient structure. The precise recipes remain uncertain because subtle variations in lime quality, aggregate size, water content, mixing sequence, and curing conditions dramatically influence long-term durability. Modern laboratories can reproduce individual ingredients, yet reproducing the overall performance of Roman structural concrete consistently remains an active field of materials science. Even more mysterious is what lies beneath the visible walls. Geotechnical investigations indicate that the fortress rests upon foundations showing remarkably little differential settlement, despite centuries of environmental change. Modern structural engineers understand that uneven settlement represents one of the greatest threats to heavy masonry buildings. A difference of only a few centimeters between foundation points can generate cracks propagating through entire walls. Yet Jublains displays relatively limited structural distortion considering its age and mass. Roman builders clearly understood how to distribute loads across local geology, even though no surviving engineering manuals describe exactly how they evaluated subsurface conditions before construction. The knowledge almost certainly combined practical experience, empirical observation, and generations of accumulated craftsmanship that disappeared with the collapse of Roman administration in Western Europe. The entrance system reveals another layer of sophisticated military thinking. Rather than allowing attackers to approach directly, the gateways forced anyone entering to change direction repeatedly while exposing vulnerable sides to defenders positioned above. Modern computer reconstructions demonstrate that these controlled movement corridors dramatically reduce the momentum of any assault force. Similar defensive geometry later appeared in many medieval castles, yet Jublains predates most of them by centuries. The striking question is why such advanced defensive planning was applied to a location that may never have experienced a major attack. Was the fortress designed according to standardized imperial regulations, regardless of local threat? Or were Roman engineers anticipating dangers that never materialized? The logistics required to construct the complex are almost as extraordinary as the finished building. Estimates based on wall volume suggest that tens of thousands of tons of stone had to be quarried, transported, shaped, lifted, and positioned with remarkable precision. Every cubic meter of masonry required additional lime production, itself demanding enormous quantities of firewood. Experimental archaeology indicates that producing 1 ton of quicklime can consume several tons of limestone together with substantial fuel, creating an immense supply chain extending far beyond the construction site. Roads had to remain functional, wagons maintained, animals fed, workers organized, and materials stored in carefully coordinated sequences. Without centralized administration capable of managing labor, taxation, and transportation, such a project would have been nearly impossible. At the edge of the Don River Delta, near the Sea of Azov in southern Russia, stood a Greek city built farther into the steppe than almost any other. It was called Tanais. Founded between about 290 and 260 BC, Tanais stood at the meeting point of two worlds, the Greek trading cities of the Black Sea and the nomadic peoples of the Eurasian steppe. It was not a marble city like Athens, not a buried disaster like Pompeii, and not a monumental port like Alexandria. Its mystery is quieter. It lies in trade, storage, river mud, ceramic technology, and the strange survival of objects made to carry liquid across thousands of kilometers. The site was not discovered in one dramatic moment. Ancient writers such as Strabo mention Tanais, but the ruins near modern Nedvigovka were identified and excavated mainly through modern archaeology, with large-scale research continuing from the 20th century onward. Today only a fraction of the city has been uncovered, yet the finds already show a place that functioned for nearly 8 centuries as a frontier machine of commerce, diplomacy, and engineering. Tanais was built in a difficult landscape. The Don Delta was not solid stone. It was a changing zone of silt, clay, marshland, seasonal flooding, river branches, and shifting shorelines. For a city dependent on trade, this was both opportunity and danger. Too far from the water, and ships could not reach it. Too close, and floods or erosion could destroy it. Unlike Chersonesus in Crimea, which had access to firmer coastal terrain, Tanais had to survive on a river edge where the land itself was unstable. Yet its streets, houses, fortifications and harbour-related structures suggest planning, measurement, and long-term adaptation. This is where the first technical puzzle appears. How did Greek builders choose a location that remained useful for trade for centuries in a delta landscape? Ancient surveyors had tools such as ropes, measuring rods, sighting instruments, and water levels, but they had no satellite maps, no sediment models, and no modern hydrology. Still, the city was positioned well enough to become one of the largest trade centres between Greeks and steppe nomads. UNESCO's description of the site calls Tanais the farthest northeastern extension of the Hellenic cultural sphere, and a major emporium between Greeks and nomads. Its walls tell another story. Tanais was damaged more than once, including the ravaging of the city by King Polemon at the end of the 1st century BC, and later destruction around the middle of the 3rd century AD. But after destruction, the city returned. Streets were rebuilt. Defensive lines were reused. The settlement did not simply vanish and restart as a random village. It retained a memory of layout. That implies preserved survey points, surviving foundations, or a practical building tradition passed from one generation to the next. In Pompeii, urban planning was frozen by volcanic ash in AD 79. In Tanais, the challenge was different. Planning had to survive violence, abandonment, rebuilding, and a moving river environment. The building materials add another layer. Tanais was not surrounded by endless high-quality building stone. Large stones, roof tiles, timber, clay, metal fittings, fuel, food, and water all had to move through a logistical network. Every wall block was not just a stone, it was evidence of transport. Every repaired tower meant quarrying, hauling, storage, and labour control. In a frontier city, this matters. A place like Alexandria could rely on imperial-scale infrastructure and Mediterranean shipping. Tanais operated at the border of the Greek world, where roads, rivers, carts, animals, and political agreements all had to work together. But the most revealing technology at Tanais may not be its walls, it is the amphora. At first glance, an amphora looks simple. A clay jar with 2 handles, a narrow neck, and a pointed or rounded base. But in the ancient world, amphorae were industrial containers. They were the shipping barrels, fuel tanks, wine bottles, oil drums, and customs labels of the Mediterranean and Black Sea economy. Thousands of fragments from sites like Tanais are not just broken pottery. They are data. Their clay fabric, shape, stamp, residue, and repair marks can reveal origin, contents, trade routes, taxation, and even preservation technology. Tanais received amphorae from across the Black Sea world. Sinope, Rhodes, Heraclea, Pontica, Chersonesus, and other production centres. Many carried wine, olive oil, fish products, or other liquid goods. Compared with inland settlements of the steppe, this is extraordinary. Amphorae were heavy, fragile, and expensive to transport. A large transport amphora could hold roughly 20 to 40 litres, depending on type, and when filled with wine or oil it could weigh more than 40 kilograms. Moving hundreds or thousands of them required ships, docks, storage yards, counting systems, and handlers who knew how to stack fragile containers without losing the cargo. The mystery is not whether Tanais traded. The mystery is how precisely that trade was controlled. Many amphorae were stamped before firing. These stamps could include names of officials, manufacturers, workshops, or production centres. In the Black Sea region, stamped amphora handles are one of the strongest pieces of evidence for commercial links, especially with places such as Sinope and Chersonesus. They worked almost like ancient tracking codes. A stamped handle could tell archaeologists where the container came from and sometimes narrow its date to a specific period. But this also means ancient merchants were not moving anonymous jars. They were moving standardized goods through a system that required trust, weight control, volume expectation, and legal recognition across cultures. Then comes the deeper technical question. How were these amphorae made reliable enough to preserve liquids over long journeys? Clay is porous. A fired ceramic vessel can still absorb liquid through microscopic pores unless the clay body is dense enough, the firing temperature high enough, or the interior is coated. Ancient amphora production required careful clay selection, levigation, temper control, wheel forming, drying, and firing. Typical ancient ceramic firing often reached roughly 800 to 1000 degrees Celsius, depending on kiln type, fuel, and atmosphere. Too low, and the vessel remained weak and porous. Too high, and the amphora could warp, crack, or vitrify unevenly. The potter had to control temperature without thermometers. That alone is impressive, but liquid storage demanded more. Many amphorae used organic linings, pine resin, pitch, wax, bitumen, oils, lime mixtures, or combinations that varied by region and cargo. Modern chemical studies of ancient amphorae use techniques such as gas chromatography, mass spectrometry, Fourier transform infrared spectroscopy, and Raman spectroscopy to detect residues invisible to the eye. These methods have identified pinaceae resins, heated pitch markers, fatty acids, oils, and other compounds in ancient ceramic containers. In simple terms, the jar was not just fired clay, it was a composite storage technology. This is where Tanais becomes fascinating. A frontier city receiving imported amphorae also received invisible chemical engineering. Wine shipped from the Aegean or southern Black Sea did not survive only because of the jar shape. It survived because the interior surface may have been sealed, disinfected, flavored, or protected by resinous coatings. Pine resin could reduce leakage and slow spoilage. Pitch could waterproof the ceramic. Wax could help seal stoppers. Bitumen could provide a strong barrier in some regions. Lime and oil mixtures could form water-resistant compounds. But the exact recipes were rarely written down, and organic materials decay, oxidize, or chemically transform over 2,000 years. So archaeologists face a paradox. The amphora survives, the technology inside it often does not. Imagine a ship arriving near Tanais with hundreds of amphorae. Each jar had to be formed to a recognizable standard, fired without fatal cracks, lined with a substance suitable for the cargo, sealed at the mouth, marked or stamped, loaded into a ship, cushioned by packing material, unloaded near the Don, stored through seasonal temperature changes, and then sold or redistributed to nomadic groups of the steppe. In winter, the region could freeze. In summer, heat could expand liquids and stress seals. A poor stopper could ruin wine. A porous wall could leak oil. A wrong resin could alter flavor. A weak jar could break during transport. This was not primitive trade. It was applied material science. The shape itself was engineering. Narrow necks reduced evaporation and made sealing easier. Handles allowed lifting, tying, and pouring. Pointed bases could be packed into ship holds using sand racks or layered cargo arrangements. Similar shapes across the Mediterranean were not artistic coincidence. They were solutions to repeated transport problems. A jar had to fit the human body, the ship's hold, the warehouse floor, and the merchant's accounting system. Yet at Tanais, the amphora raises questions that remain difficult to answer. Were empty jars reused locally? Were broken amphorae recycled into building material, drainage fill, or floor packing? Did merchants at Tanais refill imported containers with local products? Could steppe traders recognize stamps and trust them as quality marks? How much of the city's economy depended on amphora-based goods? rather than grain, hides, slaves, livestock, or metals. Archaeology can count fragments, classify forms, and analyze residues, but it cannot fully restore the daily intelligence behind the system. Even preservation itself is uncertain. When a residue test identifies resin, it does not always reveal the full recipe. Was the resin boiled once or repeatedly heated? Was it mixed with beeswax? Was the vessel warmed before coating? Was the lining brushed, poured, smoked, or rotated inside the jar? Did different cargoes require different coatings? Fish sauce, wine, and oil do not behave the same way. Garum-like fish products are salty, chemically aggressive, and strongly scented. Wine is acidic and sensitive to oxidation. Olive oil can become rancid. Each cargo demanded different protection. Deva Fortress rises above the city of Deva in Hunedoara County, western Romania, on Fortress Hill, a volcanic height overlooking the Mureș River Valley. The citadel is usually dated to the middle of the 13th century, with early references around Castrum Deva, and it was built on a hill recorded at about 371 to 378 meters high. Several local historical sources connect the hill with older Dacian occupation, while geological descriptions place its formation in Neogene volcanic activity, roughly 10 to 6 million years ago. That is the first strange fact. This was not a comfortable building site. It was a hard volcanic mass, steep, exposed, and difficult to supply. Yet medieval engineers turned it into one of Transylvania's strongest defensive points. The discovery of Deva Fortress is not the story of one archaeologist finding a lost ruin in the forest. It is the story of a fortress that never fully disappeared. It stood above Deva for centuries, visible from the town, damaged by war, repaired, abandoned, and restored again. Written sources mention the fortress from the 13th century, and later records show it changing function from military stronghold to noble residence and garrison. In 1453, John Hunyadi transformed it into a noble castle, strengthening its status in Transylvania. By the 15th to 17th centuries, many of the walls visible today had taken shape, including defensive chambers, gates, towers, and the central upper area. What makes Deva mysterious is not that nobody knows who built it. The mystery is technical. Why choose a volcanic hill so difficult to build on? Why force stone, lime, timber, water, weapons, food, and labor up a steep isolated height when easier locations existed nearby? The obvious answer is defense. From the summit, guards could observe the Mureș Valley, one of the important movement corridors of Transylvania. But defense alone does not explain the engineering. A fortress must not only see danger, it must survive weather, siege, fire, supply shortage, and the slow movement of unstable ground. The volcanic hill itself is the first hidden machine. Unlike soft earthworks, a volcanic neck gives strength, height, and visibility, but it also creates serious problems. Hard rock is difficult to cut. Irregular surfaces make foundations complicated. Natural fractures can guide water into walls. Steep slopes make collapse more dangerous. Medieval builders had no modern geotechnical survey, no laser scanning, no concrete anchors, no powered cranes. Yet the fortress was adapted to the rock instead of being forced into a perfect geometric plan. Its walls bend with the hill, its defensive belts follow the terrain, its gates and towers appear where the landscape allows control. This suggests a practical understanding of load, slope, and stone behavior that was never written down in a surviving engineering manual. The greatest unsolved question is logistics. A wall 2 meters thick is not only a wall, it is a supply chain frozen into stone. Every block had to be quarried, selected, carried, lifted, placed, and bound. Lime mortar required limestone or suitable raw material, fuel for burning, water for slaking, and skilled mixing. Timber was needed for scaffolding, gates, roofs, hoists, and temporary supports. Metal was needed for tools, hinges, weapons, and reinforcement. Even if some stone came directly from the hill, builders still had to shape it and move it across steep ground. If material came from below, then the problem became even greater. Today, visitors can climb by modern paths or cable car, but medieval workers had only animals, human carriers, sledges, ropes, and timber frames. The fortress seems to have solved this through phased construction rather than one impossible campaign. Deva was not built in a single moment. It changed across centuries. That makes the engineering more impressive, not less. Each generation had to attach new work to older work without destroying the stability of the hilltop. The visible remains include belts of fortified walls, gates, towers, the ruins of a palace and guard rooms. Such a layout required not only military thinking but long-term spatial planning. Builders had to know where pressure would move, where attackers would be slowed, where defenders could fire, where people could gather, and where supplies could be stored. Water may be the quietest and most dangerous mystery. A hill fortress without reliable water is only strong until thirst begins. Deva's summit has no easy river or spring like the valley below. A garrison needed drinking water, cooking water, water for animals, mortar preparation, cleaning, and fire control. In a siege, this requirement could become fatal. Medieval hilltop fortresses often depended on cisterns, rainwater collection, storage pits, and carefully protected wells. But at Deva, the complete system is still difficult to reconstruct from the surviving ruins. The question is not simply whether water existed. The question is how much could be stored, how it was kept clean, how leakage was prevented on fractured volcanic rock, and how long the fortress could resist if cut off from the town below. The defensive design also raises questions. Deva was not just a wall around a summit. It had multiple chambers, gates, towers, and inner zones. This meant an attacker could not simply break one barrier and control the fortress. They had to pass through controlled spaces, changing elevation, exposed to defenders from several directions. The hill itself became part of the weapon. Narrow access routes slowed movement. Curved walls limited direct assault. Higher positions allowed observation and fire. The fortress was a stone system built around gravity. In modern military terms, it looks like defense in depth, but in medieval practice, it came from experience, memory, and repeated adaptation to real attacks. The later history of Deva gives the structure one accidental test. During the 1848 to 1849 revolutionary period, Austrian soldiers occupied the fortress. In August 1849, an explosion in the ammunition or gunpowder storage destroyed a large part of the citadel and killed soldiers inside. Some accounts place the event on the 13th of August. For a medieval fortress, this was catastrophic, yet parts of the walls, towers, and defensive belts survived enough to remain visible and later be restored. That survival matters. An internal explosion attacks a structure differently from a siege. It pushes outward from inside, where walls were not designed to receive the same kind of force. The remaining ruins suggest that the fortress was not a fragile shell, but a massive system tied deeply to the hill. There is another unanswered issue. How much older knowledge lies beneath the medieval fortress? Local historical descriptions say Deva was built on an earlier Dacian site, and the wider region contains traces of Bronze Age, Dacian, Roman, and medieval occupation. The Dacian word Deva itself is often associated with fortified settlements. If the medieval builders reused an older strategic place, then Deva may preserve a layered memory of defense. The 13th century fortress did not appear in an empty landscape. It rose in a region already shaped by mining, roads, valleys, and older fortified traditions.
but the exact relationship between older occupation and the medieval walls remains a difficult archaeological question. Citania de Brateros was brought into archaeological history in the 1870s when Francisco Martín Sarmiento began systematic excavations on Monte de São Romão, near Guimarães in northern Portugal. What he uncovered was not a simple hill village, but a vast Iron Age settlement overlooking the Ave River Valley. About 24 hectares in total, with roughly 7 hectares of visible excavated ruins today. The site is now considered one of the most expressive proto-historic settlements of the Iberian Peninsula, remarkable for its walls, urban layout and architecture. At first glance, Citania de Brateros looks like a ruined city of stone circles and broken walls. But the longer we look, the stranger it becomes. This was a Castro culture settlement, built mainly before full Roman control of the region, yet its organization does not feel random. Streets run through the hilltop in a roughly planned pattern. Residential areas, public zones, paved roads, livestock spaces, ramparts, gates and bath structures were arranged across difficult terrain. In many Iron Age settlements, architecture appears to grow outward through necessity. At Brateros, the city seems to have been negotiated with the mountain itself. The first technical puzzle is the stone. Brateros was built largely from granite, a hard igneous rock with a Mohs hardness of around 6 to 7. It is not easy material. Granite resists shaping, dulls tools, and weighs roughly 2.6 to 2.8 tons per cubic meter. A single block, only half a cubic meter in volume, could weigh well over 1 ton. Yet thousands of stones were quarried, moved, fitted and stacked across a hilltop without modern cranes, steel saws or cement. The walls were built using dry stone masonry, meaning no mortar held them together. Stability came from weight, friction, careful placement, and the silent intelligence of the builders. This matters because dry stone construction is unforgiving. If a wall leans too far, water enters. If stones are badly seated, pressure concentrates in weak points. If the foundation shifts, the structure opens and collapses. At Brateros, several ramparts still survive, and some walls are reported between 1 and 3 meters thick, with restored sections reaching almost 4 meters high. The settlement was protected by multiple defensive wall lines, including a partly preserved 4th line to the north, and these walls also shaped circulation through gates, ramps, and stairs. They were not only barriers, they were instruments of control. The question is not whether Iron Age people could build with stone. They clearly could. The question is how they controlled error at this scale. In Roman engineering, we often find written traditions, standardized military surveying, trained architects, and administrative records. At Brateros, there is no surviving manual, no construction plan, no inscription explaining who measured the walls, who chose the stone, or how labor was organized. Yet the site required quarrying, transport, road access, foundation preparation, drainage awareness, and repeated building standards across generations. The urban layout deepens the problem. Brateros was not a collection of isolated huts scattered over a hill. It contained many circular houses, some rectangular structures, paved streets, courtyards, and compounds. The settlement's acropolis occupied an elevated area of about 7 hectares, and the broader site extended over a much larger fortified zone. Some streets appear carefully arranged rather than merely worn by movement. Compared with smaller hill forts, Brateros feels almost proto-urban. Compared with Roman towns, it lacks the rigid geometry of a military grid. That middle condition is what makes it fascinating. It suggests a society that had planning principles, but not necessarily the same planning language as Rome. Then comes the hidden engineering of water. Northern Portugal is not a dry desert where ruins survive because rain rarely falls. The region has a wet Atlantic climate. On a hilltop settlement, water is both a resource and a threat. Rain running down stone streets can erode foundations, flood interiors, and destabilize walls. Yet Brateros remained occupied long enough to develop a complex built environment. Paved streets and stone compounds imply that water had to be guided, slowed, drained, or absorbed. Some channels and drainage features are known, but the complete operating system is still difficult to reconstruct. The most important parts may have vanished. Wooden covers, soil channels, organic roofing, perishable gutters, or surface treatments erased by time. The houses create another unanswered question. Many are round, a form common in Castro culture. Round buildings distribute lateral pressure efficiently and can be easier to roof with conical timber structures. But Brateros also shows rectangular and mixed forms, suggesting changing function, social difference, Roman influence, or experimentation. Roofs are the missing half of the city. Stone walls survived. Timber, thatch, and clay disappeared. Without the roofs, archaeologists must reconstruct the ancient city from its skeleton. We do not know exactly how smoke escaped, how interiors were insulated, how roofs resisted Atlantic storms, or how much woodworking expertise was required to complete what the stone foundations began. The most haunting structure at Citania de Brateros is the Pedra Formosa, the beautiful stone. It belonged to a Castro bath complex, often interpreted as a sauna or ritual bathing structure. Archaeology magazine notes that a bath complex dating before Roman annexation of the region in 19 BC was found at Brateros in the 1930s, with a decorated stone slab and evidence connected to water supplied from a nearby spring. This is where Brateros becomes more than a fortified town. If the bath was truly a steam structure, then the builders were not only shaping stone, they were managing heat, water, air, and ritual movement. Similar Iron Age sauna-like buildings are known in northern Portugal and the Cantabrian regions of Spain, but they remain under-discussed compared with Roman baths. Researchers have described them as specialized buildings found in large hill forts, possibly connected with bathing, purification, protection, and ritual practice. The technical mystery is how the system worked in practice. A steam bath requires more than a closed room. It needs controlled heating, water delivery, ventilation, drainage, and safe human access. Too much heat makes the chamber dangerous. Too little heat makes the ritual ineffective. Too much smoke makes it unusable. Too much trapped moisture damages the structure. The builders had to understand how stone stores heat, how water turns to vapor, how air moves through small openings, and how bodies experience temperature. This is practical physics, but without equations, thermometers, or written engineering theory. The Pedra Formosa itself makes the puzzle even stranger. It is not merely functional, it is decorated. Its carved front suggests that the bath was not a hidden utility, but a meaningful threshold. The person entering may have crossed from ordinary space into a controlled ritual environment. The stone worked like architecture, sculpture, and technology at the same time. In Roman baths, engineering is displayed through vaults, hypocaust floors, aqueducts, and pools. At Brateros, the technology is more compressed and more symbolic. A stone doorway, a heated chamber, water, darkness, steam, and controlled passage.